So then I think let the last people take a seat. We have everybody on board that we expected for today. Thanks a lot for coming to Berlin. Welcome Berlin, welcome from Berlin to the audience remote. We have our midterm event for project KI data tooling. And on behalf of my co-leads, Armin Koehler from Bosch and Professor von Köster from DLR and the whole consortium, I welcome you here in Berlin for this event today. It's going to be an exciting discussion continuing from yesterday, where we saw extensive results from the KI Absicherung project looking into safety argumentation and also the role of scientific data. I think we concluded yesterday with one of the questions regarding how good will the data have to be, the synthetic data and the data that we generate to train our deep neural networks that we use for automated driving functions. And that's, of course, one of the major questions that we're going to deal with today. Methods to create data, methods to manage and optimize the data, how to deal with an important and efficient mix of synthetic and real data to achieve the goals that we all want to see in the end, which is safe, reliable, highly performant, automated driving functions and driver assistance functions out on the road. That also implies, of course, not only high-quality technical discussions and high-quality technical means, but it also involves, of course, a bit of a view into how do we comply with regulations. How do we comply with standards that are being used as state-of-the-art minimum that we also heard about yesterday with the impressive standardization initiatives that are now being generated to regulate, to help regulate the AI use in automated driving functions. And I think tooling, all in all, will have an important contribution. Tooling will help to generate those development processes that we're going to have in the future. Tooling will have to play an important role in reproducibility and generating the quality and reliability in the data-driven development processes that we're going to see. And hence I'm very much looking forward to the discussion today. We try to make it a very interactive format for those discussions. So we try to bring down the plenary speaking part down to what we saw as a minimum to get you informed about the latest progress and midterm status of the project. And we try to bring up the discussion and the interaction as much as we could see possible in the program. So I encourage you very much to participate, to ask questions, and we're also with the podium discussions and the panel participants that we're going to have today. I think we're all going to kick off hopefully a lively debate on the role of data and the tools and the means to create and manage those data. So without further ado, let me also specifically welcome our representatives from the government and the project bearers, Stefan Heidemann from the department EVA3 at the German Ministry, Federal Ministry of Economics and Climate Affairs. He's going to be giving a short introductory address today as well. So good morning, Mr. Heidemann. And also let me welcome here in the room Frau Riedorf, Mrs. Riedorf, and also remotely Hannes Oehmann from the TÜV Rheinland, representatives of the project bearer working together. So, Mr. Heidemann, we thank you very much that you were able to make it for today. I know you had some very special constraints this week, which made it seem impossible until yesterday. But thank you very much. Welcome to the team today. And hopefully we'll see you around for a bit. And you'll be able to participate in listening to the talks as much as possible. Your floor, Mr. Heidemann.
Thank you very much. Can you hear me?
Yes.
Okay. Ich halte meinen Vortrag auf Deutsch. Verschone Sie von meinem Englisch am frühen Morgen. Es tut mir absolut leid und ich bedauere sehr, dass ich nicht bei Ihnen sein kann. Mich hat die Corona-Quarantäne erwischt und das ist aus diesen Gründen leider verbaut. Ich grüße Sie ganz herzlich von Herrn Stöckel-Puckal, meinem Referatsleiter, der heute leider nicht da sein kann. Vielleicht zu meiner Person ganz kurz, dass Sie wissen, mit wem Sie hier sprechen. Ich bin der Nachfolger von Herrn Marx, der Ihnen vielleicht ein Begriff ist. Ich bin der Fachreferent seit 1.6., also ganz frisch dabei, für diese Förderprogramme im Automobilbereich. Und ich habe vorher schon ganz, ganz viele Investitionsprogramme betreut. Ich bin Förderexperte und das ist für mich jetzt neu, die Forschungs- und Entwicklungsförderung. Und das habe ich mir auch ganz bewusst ausgesucht, weil ich den Bereich sehr interessant finde und auch ein Faible für Autos und Automobilbereich habe. Vielleicht fragen Sie sich, und ich habe mir überlegt, was erzähle ich Ihnen, wie begrüße ich Sie? Sie sind ja die Experten, Sie kennen das Programm besser als ich. Und ich habe mich gefragt, vielleicht fragen Sie sich, was macht denn eigentlich so ein Ministerium? Wir sind ja die Zuwendung geben, die das Projekt mit Ihnen gemeinsam in Kombination ermöglichen. Und würde da ganz kurz mal ein paar Worte verlieren wollen, um Ihnen zu erklären, wie unsere Rolle ist und warum wir dieses Projekt so wichtig erachten. Und das ist übrigens, will das vorwegschicken, auch der Grund, warum ich mich entschlossen habe, trotz Schnupfen und Corona einfach Hallo zu sagen, einfach die Wertschätzung unsererseits für Ihr Projekt auch rüberzubringen. Das ist mir ganz besonders wichtig. Was macht so ein Fachreferat? So ein Fachreferat, wir sind das Fachreferat für Digitalisierung, Industrie 4.0, ganz fein. Wir kümmern uns um verschiedenste Themen im Bereich Digitalisierung, Industrie 4.0 und ein Riesenblock macht halt die Automobilindustrie aus. Meine Aufgabe ist zum Beispiel, ein Förderprogramm aufzusetzen, und zwar so, dass es haushaltsrechtlich funktioniert. Darauf können Sie sich dann bewerben, so haben Sie es ja auch getan. Und dann werden Sie ausgewählt, wenn das Projekt gut ist, wir es für gut erachten. Und dann begleiten wir das Projekt. Und meine Aufgabe ist daran, erstmal sicherzustellen, dass Sie das Geld bekommen, dass das Geld auch in unseren Töpfen bleibt, damit wir die Förderprogramme machen können und vor allem die strategische Steuerung. Ich war gestern schon bei der, oder habe zugeschaut aus dem Homeoffice, aus der Quarantänesituation, gestern bei der Veranstaltung KI-Absicherung und war wirklich sehr beeindruckt, wie tief Sie da in die Themen gegangen sind. Und natürlich sind Sie die Experten und wir brauchen auch auf unserer Seite natürlich Experten, die diese Förderanträge analysieren, betrachten und uns vorlegen und auswerten. Und das macht für uns der TÜV Rheinland. An dieser Stelle auch ganz herzlichen Dank an Herrn Oehlmann, der mir auch ein paar Sachen jetzt zu Ihrem Projekt aufbereitet hat. Wenn man sich die Zahlen anschaut, will ich ruhig noch mal verlieren, dann ist ja diese ganze KI-Familie über 100, also rund 115 Millionen Euro Projektvolumen. Das BMWK unterstützt das mit 59%. Das bedeutet aber auch, dass auf der anderen Seite 40% andere tragen. Und alleine das zeigt schon in diesen Dimensionen, dass nicht nur wir an dieses Projekt glauben, sondern auch die restliche Summe finanzieren. Und dieses KI-Data-Tooling nimmt ja in dieser KI-Familie auch einen essentiellen Stand ein, mit über 25 Millionen und wir fördern das Projekt mit 16 Millionen. So, jetzt ist es meine Aufgabe teilweise auch, den Leuten draußen zu erklären oder den Entscheidungsträgern bei uns im Haus zu erklären, was sie da eigentlich machen. Ja, wenn man sich gestern zum Beispiel in der Diskussion KI-Absicherung, wenn ich da jetzt zum Beispiel bei uns einen Entscheidungsträger reinsetzen würde, würde mich fragen, Herr Heidemann, können Sie mir das mal einfach erläutern? Und ich habe mir überlegt, vielleicht ist das eine lustige Anekdote, weil ich brauche Ihnen ja nicht erzählen, was Sie im Projekt gemacht haben, aber was ich erlebt habe, als kleine Auflockerung und dann können Sie gerne in die vertiefte Diskussion gehen. Und zwar habe ich teilgenommen an einem Fachgespräch von Ingenieuren, die politischen Entscheidungsträgern das autonome Fahren erklären sollten. Und da wurde erstmal angefangen mit der Sensorik. Da wurde erklärt, was ist Ultraschall, was macht Radar, was macht LIDAR. Dann entspann sich eine Diskussion, warum vielleicht Radar demnächst gar nicht mehr so wichtig ist. Und irgendwann sagte ein Ingenieur, aber eigentlich, ich meine, wir Ingenieure würden am liebsten das Auto mit allem Möglichen vollpacken, mit so viel Sensorik wie geht. Aber grundsätzlich trauen wir dem Menschen beim autonomen Fahren immer noch mehr zu als dieser ganzen Sensorik. Und das, wenn man sich betrachtet, dass der Mensch eigentlich nur zwei Augen hat, ein Augenpaar, das kann noch nicht mal rundum sehen, kann noch nicht mal besonders weit sehen, ist gestört durch Lichteinflüsse und trotzdem vertrauen wir den Menschen im Moment noch mehr zu als diesem ganzen Assistenzsystem. Warum ist das so? Die Lösung ist ganz klar, weil das, was hier oben sitzt, anscheinend diese beschränkte Sensorik doch so gut unterstützen kann, dass wir denken, dass man besser fahren kann als im Moment die Systeme, die auf dem Markt sind. Was bedeutet das? Und deswegen habe ich das Beispiel gebracht. Zum einen zeigt es die Bedeutung der Daten, der künstlichen Intelligenz. Und zum anderen finde ich dieses Beispiel auch sehr schön, dass man den Leuten natürlich draußen auch erzählen muss, was sie Großartiges hier tun. Denn dass autonomes Fahren in der Zukunft ein Riesenmarkt ist und viele Dinge erleichtern wird, das liegt ja auf der Hand. Aber wie wird das sichergestellt? Wie können wir das machen? Und da sind wir wieder bei Ihrem Projekt. Ihr Projekt ist ja auch geprägt gewesen von Corona. Sie sind mehrere Player, 9 Unternehmen, 8 wissenschaftliche Partner. Das sind erschwerte Bedingungen. Und trotzdem haben Sie jetzt zu diesem Midterm-Event schon tolle Ergebnisse geliefert. Wir sind da sehr zufrieden und sehen auch, dass Ihr Teilprojekt in der KI-Familie ein sehr innovatives Projekt ist und einen essentiellen Bestandteil hierbei einnimmt. Und ich kann immer nur wieder betonen, künstliche Intelligenz ist schon per se schwer greifbar. Aber viel wichtiger ist natürlich auch, was passiert mit den Daten, die die künstliche Intelligenz nutzt. Wie gut trainieren wir diese Daten? Wie gut sind diese abgesichert? Und welche Sprünge können wir vielleicht hier erwarten? Ich war auf einer Fachtagung, da wurde diskutiert, ja, wann können wir denn endlich uns ins Auto setzen, ich mit meinen Kindern spielen und das Auto fährt mich einfach von A nach B. Da wurde die Frage an Experten gestellt, was denken Sie denn, wie lange dauert das denn noch? Und das war ganz erstaunlich, dass da Ingenieure gesagt haben, das dauert noch mindestens 10 Jahre, wenn nicht sogar mehr. Und andere sagten, naja, wer weiß, welche Entwicklungssprünge wir im Rahmen der künstlichen Intelligenz in Zukunft tun. Und vielleicht sind wir da schneller am Ziel, als wir denken. Und dieser Bereich ist so spannend, den Sie gerade machen. Es hat so große Auswirkungen und ja nicht nur fürs automobile Fahren, sondern das, was Sie entwickeln, hat ja einen Overlap auf viele andere Bereiche auch. Und deswegen sind wir sehr, sehr froh, dass wir dieses Projekt fördern können, dass die Partner am Start sind und sie haben da unsere Unterstützung, unsere Wertschätzung und wir freuen uns da sehr. Ich wünsche allen Beteiligten heute ganz viel Freude und viel Spaß an der Sitzung. Ich selbst muss gleich kurz weg. Nehmen Sie mir das nicht persönlich. Wir kümmern uns gerade um ein anderes Modul, da brennt es. Da kratze ich gerade jeden Euro zusammen unter Wahrung aller Haushaltsregeln, damit die letzten Projekte noch finanziert werden können. Danach bin ich aber wieder dabei, folge dem Stream. Ich freue mich sehr. Bedauere nochmal sehr, dass ich nicht vor Ort sein kann. Ich hätte gerne die Fachgespräche einfach mal geführt, um auch besser in die Themen zu kommen. Nichtsdestotrotz eine ganz tolle Diskussion, einen weiteren guten Verlauf für das Projekt und einen ganz tollen Tag. Vielen Dank.
Herr Heidemann, ich antworte jetzt einfach noch mal kurz auf Deutsch. Vielen herzlichen Dank für die tollen Vorschusslorbeeren. Wir hoffen, wir können den Erwartungen heute gerecht werden und Ihnen dann auch viel Material liefern für die Diskussion, die Sie weiterhin im Ministerium auch haben werden. Wir sind uns sicher, momentan sind alle Haushaltsfragestellungen sicher nicht einfach zu diskutieren mit turbulenten Randbedingungen. Und deswegen freuen wir uns sehr auch über Ihre Unterstützung und Ihre Hingabe auch für die KI und für die Themen, die da mit verbunden sind. Wir hoffen, dass wir dann am Ende auch viel Material liefern für eine KI-Strategie 4.0 der Bundesregierung. Auf die freuen wir uns dann auch schon ganz arg. Und vielen Dank, dass Sie dann heute nochmal auch mit reinschauen. Die physischen Diskussionen und Fachgespräche holen wir so bald wie möglich nach. Freue mich auch schon sehr drauf. Bis später. Ansonsten auch gute Besserung weiterhin. So let's get back to our English language track. We had the welcome from a government, and I'd like to quickly now hand over to our first guest speaker. Unfortunately, due to travel constraints and time zone differences, we have a pre-recorded speech by Mr. Norm Marks. He's head of automotive industry, the global director of automotive industry business at Nvidia. He's going to give us an introduction on synthetic data generation and how it accelerates AV development and testing. I think Nvidia has lately demonstrated tremendous progress in their efforts and has also published great results that we're very curious to see more of. And then I would like to hand over to Norm Marks and listen to his talk. Have his video, please.
Hello, everyone. I'm Norm Marks from Nvidia. I lead our global automotive enterprise business, so I have the great pleasure of engaging deeply across many of the companies in the industry and look forward to sharing with you today some of the work that we're doing around synthetic data generation and how we see this is truly going to be able to accelerate AV development and testing. I know I won't be the only talk today on synthetic data generation. You'll have another one later in the day, and in fact, a deep dive session for some of you. So let me go ahead and kick things off and begin to share a brief set of materials with you. Apologies that I couldn't be there in person, but I hope you find what we'll share with you interesting for today. Okay, so to begin with, let's talk about the end-to-end development flow that I'm sure all of us are familiar with. I'll be talking about synthetic data generation today and how it augments real-world data. But of course, we all have been instituting data collection operations for real-world data so that we can pull that in, label and process the data that's useful, use mapping to be able to help in our AV development efforts, ultimately build a great many deep neural networks, and eventually deploy those as the AV software stack or autopilot, as some call it, for the self-driving functions. We want to test that against scenarios like NCAP, obviously important for those of us here in Europe, and remote parking and all the other automated parking routines. We're really excited about the opportunities for AI cockpits of the future, a talk for a different day, and then ultimately validation is so important to ensure that we have safe self-driving vehicles on the road. To just give you a sense of the scale of the massive amount of efforts that we have been doing over the years here at Nvidia, we have thousands of engineers building these deep neural networks, and we now have hundreds of thousands of hours of real-world data, hundreds of millions of frames. We're collecting 10 petabytes of data per week, 1,500 labelers, ultimately resulting in over 50 million labeled images for training deep neural networks. And we do that training on thousands of DGXs on our Saturn V supercomputer. We then use both replay and simulation for validation and testing. You know, tens of millions of virtual miles driven already on hundreds of what we call drive constellations for our hardware in the loop setting. But I really just wanted to set the stage there with our efforts. And now I'll just kind of break it down. If I'm an individual company, what might that look like? As I mentioned, 10 petabytes per week results in roughly 2 petabytes a day. This varies, of course, based on the number of cameras, radar, and LiDAR that you're using and the quality of the cameras. And then we curate about 10% of that data that's useful. You know, if I'm driving straight on a highway for a long period of time, I won't need every single frame. Some of the quality won't be good. In other cases, we might be applying active learning. So if I've already spotted, say, that pink elephant, well, then I don't need to label it again. But the data that is useful, we pass on to labeling efforts. As I mentioned, we have over 1,500 workers, over 50 plus projects active at any given time. Goal, of course, is always ensuring the highest possible quality per frame with what's possible with human labeling. More on that as we talk about the impacts of SDG. On the training side, we're building 20 or more deep neural networks, and we know that from an industry perspective, it will take a great many. Tesla's talked about building 48 networks in some of their talks. We've got hundreds of engineers that we're constantly optimizing, in our case, over 50 or more parallel experiments on any given day with each one of those networks. Now, the biggest range I see in the industry is around replay. If you're like us, you're testing thousands of hours every day. You want to iterate quickly. I know we have some customers, a robotaxi in particular, that's testing hundreds of thousands of hours. Now, of course, they take more time for that data to be processed, but they're rerunning all that real world data that they've collected to be able to test rigorously against the AI. And then we all know the power of simulation, which I'll talk briefly about today, to test potentially 100 million global driving scenarios and billions of miles, things that would take hundreds of vehicles, hundreds of years to be able to do otherwise. And that's made possible by solutions like DriveSim, our AV simulator built on top of Omniverse. It's cloud native, so it can allow for a variety of different flexible ways to deploy and scale up in the data center. We want to ensure that we have repeatable and reproducible scenarios, and so that's built in from the core with DriveSim. It's scalable, as I mentioned. You can scale up in the data center as many virtual vehicles are needed for software in the loop or hardware in the loop testing. And we've built it as a very open modular platform. So if you're using other solutions in a simulation tool chain, you can use the APIs in DriveSim to plug those in, connect to them, and be able to have those run. Now, there are 4 different use cases in DriveSim. I'm going to spend most of the time today on synthetic data generation, but we also have planning and control for software in the loop. We can run the full AV stack in either software in the loop or hardware in the loop mode. And then we can also test the virtual vehicle in hardware in the loop mode and even bring in things like testing the interior cockpit. Now, today I want to talk about Nvidia Drive Replicator, which is our synthetic data generation engine. It allows for a new type of ground truth, things that humans can't label or that real sensors can't capture. But the real beauty of it is it's fully programmable. So you can have control over the data types and the distribution of them, which is so important in this case. For example, we can go out and find those long tail events that maybe we wouldn't want to send a real data collection car out there. For example, you wouldn't, I hope, want me riding on a bicycle in front of a vehicle driving at 80 miles an hour. And then the real beauty of it as well is that it's pixel accurate. We won't have any human errors from labeling, and there's no restriction on the data. And we can get features that sensors don't capture as well. So it might be useful to actually see this in action. So hopefully the video comes through okay for you here. So let me just run a sense of seeing data that was generated by Drive Replicator. In our case, this is on what Nvidia calls our Hyperion sensor kit. So our configuration of camera, radar, and LiDAR. So let's give it a show. So here we're seeing bounding boxes and even 4D ground truth that you see on the left. And we can also bring in LiDAR and radar into the synthetic data generation that we capture. Look at how complex of an event this is. This would be very difficult to schedule in the real world. We can also pick up segmentation from depth to class to instant segmentation in this. Bring in long tail events that are hard, like occluded pedestrians, and then to be able to accelerate the amount of data that we're creating, we bring in domain randomization. You see the pillars and the shopping carts coming in. And so we can take one scene and create so many different versions of it. This too helps greatly with the ability to be able to scale up. And here we're ending, giving you a sense for all the different sensors that we can be emulating with the synthetic data generation. As I mentioned, a variety of different types of segmentation that you can see here. We're seeing the cameras, as I mentioned, we can see radar and LiDAR as well. So all of this data is now available to us to ingest in and to be able to use in our AV development efforts, truly helping us accelerate the pace with which we're doing those development efforts. Let me say a little bit more about that. So one approach that could be taken, particularly if, say, there's a new project that you're taking on, or you're moving from level 2+ to level 3, or you're trying to train in a geography for the first time. We think of that as a bootstrapping effort. So you could start purely with synthetic data generation, develop the perception algorithms on that, evaluate different sensor configurations and the placement of that. I'm going to share a little bit with you as one of the use cases for where we're already applying synthetic data generation here at NVIDIA. And then set the data distribution targets. Make sure that you're getting a nice diversity across all the data types that you had. You saw in the video domain randomization as one way to be able to accelerate the distribution and diversity of the data. Ultimately, you can accelerate your development efforts here and iterate on building out the networks and testing them to see how valid they are. And then once you begin to see good efficacy of the AI, then we want to bring in sim and real data sets and really be able to improve the efficacy by having training on both. So we have real world ground truth data that we've collected. We've got synthetic data. We're training it on a mix of both. We fill in gaps with sim and or real. Either way, so we want to make sure that we cover the domain gap or any content gaps. And this becomes a very iterative process. And ultimately, we want to be able to see exactly how we can get improvements on the networks. Ultimately, this is about safe self-driving. And while I'm accentuating the ability to speed up the AV development as a result of this, imagine the benefits on speed of creating the world in a virtual environment versus having to orchestrate sending data collection vehicles out in the road. There's so much more speed that we can do to iterate quickly. We can start on day one. It's probably also worth mentioning the cost. Obviously, we can save significantly if we're using virtual vehicles to create the world as opposed to real world ones that we're sending out there. And of course, the final point is that there's no data restrictions. So if we're in a market, say, for example, that we can't move data out of, that we can accelerate by creating synthetic versions of that market. So very iterative process, a great many benefits from it. Now, the other interesting thing that we can do is we can use DNN inference to take real data sets and networks trained on them and then run them to be able to get a view to how are they working. Another very interesting visual use of synthetic data generation engine that we have with Drive Replicator. So here we'll actually show you some networks that were trained on real data sets, but now we're running them in this synthetic world. Notice on the left, we can see the bounding boxes of the labels. On the right, we can see things like free space, where I can drive in green and objects being detected in red. Here we see on the right a free parking space. So if we're working on remote parking, you can see how the network would run and we'd be able to identify that, in fact, that's a space to park. And so many other opportunities, of course, to be able to see how well are the networks running. So another very interesting use case for synthetic data generation, or at least the engine for it, where we can take a look at those networks that were trained on real data sets as well. Now, we've been using synthetic data generation at NVIDIA in our own efforts. And so let me take a few moments to just share with you some of what we're seeing in terms of the actual benefits from our own work. So 4 use cases that I'll share with you. The first one is around something that we call PathNet. And it's an interesting one for me because what you're seeing on the screen here on the left is exactly what I see when I drive the kids to school every day when I've got school runs, that bright sunrise coming at me, very difficult to see. So that certainly was one challenging use case that we wanted to be able to test against. Another one is one that you wouldn't apply data collection efforts against, and that is you wouldn't send a vehicle out to drive literally right over the middle of a lane. That's not good practice for a data collection car. But of course, it can happen in the real world. So what we wanted to do to improve our ability to be able to spot the path and the lanes is we created thousands of images of vehicles driving in the center of the lane. And then we also brought in all these difficult conditions of the angle of the sun. And we use that then to improve the ability of our networks. And in this case, with our PathNet network, we improved our mean average distance to failure by 10%. Again, safe self-driving, super important. Getting these kinds of gains to a deep neural network are absolutely go a long way towards ensuring that safety. The second thing is that you heard me mention earlier our Hyperion sensor kit. Well, when we were going from Hyperion 7 to 8, and of course this will be true for us when we go from Hyperion 8 to 9, what we were able to do with synthetic data is actually emulate the sensors even before we had them in from the sensor manufacturers. And so we generated millions of scenes before the physical sensors were available and began to build and test against those networks. And this sped up months of development efforts for us. Two other examples of deep neural networks that we improved using synthetic data. One is our ability to spot traffic lights. And we actually have a number of active POCs going with several customers right now in phase 1 deployments, squarely based on this particular network. So we know it's a challenging one. And so sometimes when we have lights at angles or they're occluded, this can be particularly difficult. And we've got to do it, of course, for all the varieties of the light, green, red, yellow. And so we, again, produced tens of thousands of images. And here we improved our ability to spot those traffic lights, particularly in those difficult scenarios, by up to almost 3%. Again, long way towards safe self-driving. And then finally, in Europe in particular, we wanted to be able to augment the real world data of signs there with synthetic data so that we could be able to improve the ability to read those sign types. Here we created 60,000 plus images, 6 different categories. We added those into the real data set. And in this case, improved our ability to spot signs by about 2%. Again, any improvement that we can make goes a long way towards safe self-driving. So again, accelerating the AV development, but also improving the efficacy of the networks themselves. Now, we know why this is so important. You've heard me mention a few times the 20 or more deep neural networks, and here you see some of those visually depicted, from obstacle detection to distance, time to collision, the opposite of obstacles, seeing free space, lane and pass, as you've heard me talk about, also traffic lights and signs, several of the places where we've already applied synthetic data generation. Weight perception's a difficult one as we're coming up on an intersection, for example. We as humans do it well. How will a safe self-driving car? And then very difficult networks like gesture and pose, I'm telling you to stop, but above me, the sign is green. How do I read that gesture and understand how to follow that? And then the AI cockpits, things like gaze and eye openness, and so many other networks, ultimately, as we monetize travel time. Now, what we're seeing is that, of course, there's no one perfect prescription for developing these networks across the various levels of driving. So to help you and others get a sense for the scale, what we've done is built a very detailed calculator based on our own observed performance of building these networks on our DGX Saturn V supercomputer. And here you see one possible path you could take over phases. And what we've done is against these networks, both ADAS and AD networks, as well as cockpit driver monitoring and interactions, we give you a sense of the phase scale of adoption in both DGXs, or the SU refers to superpod scalable units. So we're seeing from our own development efforts, 1,600 or more DGXs, 80 plus scalable units, 20 DGXs per scalable unit at the highest levels of driving. And frankly, based on the type of replay you might be doing, this can get into well over 2,000. And in fact, I'll end you with that point, just giving you a sense for what's the scale of adoption that we're seeing from an industry perspective. On the left, we're seeing a number of customers, just a few select ones, some OEMs and robo-taxis, and their scale-up journey over time over the last 5 years. And on the right, we're seeing the current state of adoption, several already reaching these high levels of scale, 2 that are already over that sort of phase 5 high level that we've given you. So I hope you found this useful. Thanks for allowing us to talk with you, and look forward to continued discussions with all of you over time.
We will convey the applause. Thanks a lot to Nvidia for the presentation today. I think this was a great impulse to kick off our day for discussions. We saw many of the topics that we're going to get back to, I think, during the day, from realistic synthetic data generation and how they can be employed in different use cases. But first of all, you already see we're changing a bit the setup here. We'd like to pick up on something that we discussed yesterday, which is collaboration between the individual projects in Germany, the publicly funded projects that we especially call a family, the KI-Familie of projects. And what we wanted to do now is pick up on the discussions from KI-Absicherung yesterday with a short panel discussion that we are going to have on the relevance of data and scenarios for the safety argumentation of automated driving systems. So largely that is the handshake between KI-Absicherung yesterday, and thanks for the great setup, Stefan, that we had already. And we hopefully will take the handshake now also in identifying the follow-up questions that we have. The panel will be moderated by Frank Köster. He's a professor and head of the institute at DLR for safe AI systems, and I welcome Frank to the panel. At the same time, he will be moderating with guests. First one will be Robert Bruckmeier from BMW. He's head of vehicle-based car functions and network AI at BMW. And will definitely contribute a good industry perspective and a strategic outlook here. And to continue with the good discussions from KI-Absicherung, Thomas Stauner from BMW, who had been leading sub-project 2 in KI-Absicherung also, will hopefully give us a bit more perspective for the discussion here on generation of synthetic data. And we're going to continue with Armin Köehler, who has both feet in one project each, in KI-Absicherung, but also in KI data tooling. Well, KI-Absicherung less, but with a lot of exposure by the Bosch colleagues at KI-Absicherung, right? And then we'll have Dr. Hardi Hungar. He's a team lead for verification and validation methods at the German Aerospace Center. Hardi will be contributing perspective from the set-level project. I think also that is an important part to be adding to the discussion, as well as the contribution from Dr. Gerhard Schunk at Valeo. He is there also on the driving assistance research team and doing the VVM methods projects. So here, I think, together then with Professor Burkhard Stiller, we'll be complementing the panel. Burkhard Stiller, we're fortunate to have you this morning. He's heading up the Institute for Intelligent Systems and Production Engineering at FZE. And then last but by no means least, we have André Rolfsmeier. He's the Director for Strategic Product Management at dSpace. And also will be contributing a perspective from model-driven engineering and simulation, with all the expertise that dSpace will be giving us here. So I think that's a great panel that you assembled, Frank. Without further ado, I hand over to you. Have fun and look forward to your discussions.
Yeah. Thank you for the introduction, also introducing the panel. So that's for me now a pleasure because I can keep things very short. We are a little bit behind the schedule, so I think we have to speed up, and I want to keep my opening statements very short. It's just for me, it's a pleasure to be part of this event because here are so many experts we urgently need to be successful in introducing AI to practical relevant applications. And then there's another thing why this is really fun for me, because I do not have to work here today. So all the other guys have to work. I'm just the question guy. I have some cards here written down, some questions. I just have to ask the questions. The experts will answer the questions, and I just have to learn today. So it's really great. And I think this should be the mood for this session now. So I want to end here with my opening statement and hand over to you, Dr. Robert Bruckmeier. So please give us also some introduction and some opening statement from your side.
Thank you very much. So it's actually a pleasure being here. Thanks for inviting and giving me the opportunity to share a few thoughts. And I'd like to structure them in 3 points, starting with product, second with technology, and third with, and that may be a little bit of a surprise, society. So let me start with product. I mean, where are we? Let's think about driving assistance systems. They were a niche product a few years ago, and now they're mainstream. They are convenient, and they increase safety, right? Now, the next level on the product side is automated driving. This is very much what we speak about here. It offers a lot more convenience, and the most precious thing we have, lifetime, right? We can do things we love to do and not drive, unless it's not safe. So safety is the key point to make this successful. And this is where I'd like to go to the second point, technology. This is the core of making the function and making it safe, right? And we all know without AI, this won't do, right? And so that's why what you do here is so instrumental and key to making this come true, right? And let me just address 2 points. One is the data tooling. We've just seen how instrumental generated data is. Especially this is on corner cases. Think about an accident scene with people lying on the street, right? It's very hard to record this real life data, and so we need to generate it. And we need all this data also to prove that the vehicle is safe. So how do we prove that? That's where KI Absicherung safety comes in. And we all know that AI systems are not predictive, not rules-based, so we need new technologies here, which you are working on to answer the key question, is the product safe? More precisely, is it safe enough? And this is where society comes in, right? Because the safe enough is about what's the society thinking about this. In the end, there's always a discussion in society, do we want this product? And under which guidelines do we want it? And now we have a lot of experience on this in the automotive industry because a car is fundamentally unsafe, right? So a century of standardization methods has helped us to get to very robust also regulation and standards and homologation methods that also apply to AI. Now, as AI is something new, we need to extend these. And that's why I think this VDA Leitinitiative is really a great constellation, because it's companies, it's research institutions, it's standardization institutions, and then also ministries working together to reach that societal consensus. What is safe enough, right? And that's what we do here. That's where we discuss, and that's where innovation happens. And now, about innovation, AI, I think, is a key enabler for innovation. And there's research around, you can find it on the internet, that AI will enable innovation on the order of 15% of the GDP, the gross national product worldwide by 2030. 15%. This is about new products, about new processes, right? It's a huge innovation potential. And now, that, of course, as I said, needs to be standardized and regulated. Now, we need to focus on using that potential and directing the regulation in a way so that the products are safe and safe enough, right? And so the emerging regulation, it's important that this is not overdone, because otherwise we will stifle the good innovation that we all need, and especially also in Germany and in Europe. We are in a global competition, and if we do this right, we can win the global competition. So these are my thoughts. Thanks for having me.
Yeah. Thank you for sharing your thoughts with us. So when I think about these different aspects, what comes to my mind is that on the different levels you mentioned, starting at the strategic level, but also when we are working really on the technologies and trying to improve them, is we cannot do it in sequence. And what we currently see is we have on these different levels currently activities. For instance, regarding the AI Act or the Data Act, and also this should be something which is helpful for us, so that is the intention. But there's always a risk to overdo some things. But you have some comment on that?
Oh, sure. And I'm not an expert on regulation, and but I spent some time on it because it's important for us how the EU regulates AI. Now, what I learned in the past months and weeks, and let me illustrate this a bit. Now, first, I think the structure is right in terms of the risk that AI brings to functions. So, in some things there is unacceptable risk, and I think some of you may have some ideas. Then there's the high-risk functions, and some things, if we speak about car accidents, are high risk, obviously, right? And then there is acceptable risk. Now, let's think about how this applies to AI. First, there's a section, what's the definition and scope of AI? And the scope is rather broad, right? And it includes things that even ancient people in Egypt have done, linear regression, right? It's proven, right? But still, it's a part of today's draft regulation. Then secondly, everything that is part of homologation is by setting of the current state is a high-risk topic and falls under very strict regulation. Now, what does that strict regulation mean? You have to prove that the data you are using is complete and correct. And there are other things. Now, let's think about what this means. I mean, completeness, let's think about the alphabet, right? 26 letters, yeah, that's complete. Now, wait a minute, there are the umlauts, and that's a sharp S. And then how about the accents, right? And then when you think about Chinese characters, there's traditional and modern, and even with characters, it's not so simple. Now let's think about texts. What is complete texts, right? Is the SMS I'm writing also necessary for completeness? Yeah. Okay. From this point, let's get to correct. Is the SMS I've been writing, is that correct? Or am I using slopper grammar? So I think that shows, even with so simple things, it's critical that this regulation is done right, and we're in the middle of this. And the documents I have seen are very long. There are many different opinions on, what's right, and how to bring this together is a huge task. And I think we need to support in that, because your expert know-how is needed to get this in the right direction, right? Because if people manage that those legal texts that do not have the scientific or the factual grounding in what this really is, then we are at the risk of over-regulating. So these are some thoughts, and I hope this energizes a bit the discussion on the direction we should be going.
Yeah, thank you. Because I think this is really great that you mentioned all these points, because I also see, in particular in these public-funded projects, we are doing some first steps with these technologies, and we try to integrate this in the best manner in the vehicle. So also not just addressing the single technologies, but also do the systems engineering, which is essential for guaranteeing safety and that stuff. And this is something where we learn some things, and this is part of our innovation process, because this will lead us to innovative products. And currently, I think it is a risk that by over-regulating some things, we are not open really to come up with innovative products, because the processes are so complex and complicated that it is really a risk that we are losing the freedom really to do some first experiments to see how it fits the best way to our products in general. So thank you for adding these things, really great. Now we have a short presentation by Thomas Stauner, also sharing some thoughts more from the perspective of the KI-Absicherungsproject. So yeah, please go ahead with your presentation.
Yeah, thank you, Frank. So I'll give you a little intro on what KI-Absicherung achieved and what we transfer further to you and what you can build up on, so to say. So the main point is that KI-Absicherung came up with an overall approach on how to do a safety argumentation for AI-based systems, in particular AI and computer vision. And that's depicted in the right upper corner here as the principal idea. So starting from the safety goal, like not overlooking a pedestrian with your computer vision system, the overall approach of KI-Absicherung basically requires you to consider how this safety goal might be affected by DNN-specific safety concerns, DNN-specific insufficiencies, like a lack of robustness or a lack of explainability. These the effect of the safety concerns on the safety goal has to be analyzed, and based on that, mitigation measures need to be brought up, and all that needs to be put down into one safety argumentation. In KI-Absicherung, a plethora of methods have been analyzed, and they're all there as a tool set, so to say. Of course, data has a paramount influence on safety of AI-based functions. So the reliance on data, in particular, is the data like complete and correct. So data coverage is a major concern, and then something which we examined in quite some detail. So in KI-Absicherung on the data side, what we did is that we developed two different tool chains to produce synthetic data with different characteristics, so to say. Overall, we produced 360,000 frames that are also provided to the sister projects in the AI family. The frames result from a close interaction between people from safety, from ML engineers and computer graphics specialists. So I think that's quite some value, and really having these three fractions in the same boat and finding a consensus on the data requirements was really unique and very important to get to the project goal. An example for this, it's not on this slide, more on the next actually, is that we designed the assets that we are using in a way which leads to some kind of coverage. Yeah? So we defined a number of prior one, so to say, attributes of pedestrians, and the assets were designed in order to cover that space that is made up from these pedestrians. Yeah, so asset generation is one thing that we give further to you, as well as data from motion capturing. All right, yeah, that's already the bridge. So what do we provide to KI data tooling on a technical level? So on the first place, that's the tool chain that we have been developing, consisting of elements from BTS, from Intel, from Bosch and Valeo. We've already been collaborating on this tool chain quite a lot. So in the tool development, like the GLTF format conversion was something that was brought in by data tooling. So thanks for that. Otherwise, our amount of assets would have been quite limited. And we also had quite some collaboration on asset sourcing, because one of our analysis results was that the amount of assets is really important to get the diversity that we need for the training. Right, so these were already collaboration topics, and there are a couple of further things that we give further to KI data tooling. There are things like our ontology, the glossary, the frames that we said. That's maybe the first most important thing that you get. With the infrastructure that you need, the data loader. Furthermore, the produced assets, the motion capturing, material measurement, which we did for the optical domain. You will get that, you can use that, and build up on it. So as further elements, we have toolchain requirements and also our labeling specification. So summing that up, I think we placed quite a lot of seeds in the ground, and there is a lot more that you can build up on it and take the harvest for all of us. So we rely on your techniques to do really data management, data generation in the scale that we need. Thank you.
Thank you, because this is really the great handover now to the overall discussion with all the other colleagues. And I want to start with a question to you. So can you characterize the specific type of risk AI introduces to safety in automated driving? So some concrete examples, because we always discuss AI as a risk here, AI as a risk there. Can you mention some concrete examples to have it in mind for also the further discussion?
Well, let me not go so much to the example level, but maybe to what is specific about ML now. So the automotive domain has quite some experience in dealing with risk that comes from malfunctioning of E/E systems. That is what is part of the ISO 26262, and it's well established. Now, in the last years, we recognize that there is also risk from performance limitations of sensors. There was the ADAS domain that motivated that, and it led to the creation of the SOTIF standard, safety of the intended functionality. And now with even more machine learning, even more AI in the product, we recognize that these functional insufficiencies do not only result from sensors the camera can see at night if there's no light. They also result from insufficiencies that the machine learning part has. So we move from a world where we had a clear rule set on how to deal with software correctness to a world where we need to address the correctness of the ML as a stochastic problem. Machine learning is stochastic. It is relying on the data set. It's an approximation problem in the end. And so also for the safety argumentation, we strongly rely now on stochastic techniques, which is simply uncommon. We've been doing that for hardware, but for software, for ML, it's a new problem which needs to be addressed. And as I said, the idea from KI-Absicherung is that we will need a combination of qualitative and quantitative arguments to really come to a complete safety argumentation. And the qualitative part, that is relying on stochastics, and I think that's what makes us sometimes feel uncomfortable, because it's simply something that we've not been doing for software.
Yeah, but to add a second question in that area is that, what do you think is AI also be able to contribute in a manner so that it raises the level of safety? Yeah. We learned that also from the introductory words from the BMWK, so that all the cognitive processes are also highly relevant, not just the sensors and that stuff. Maybe you have some opinion on that?
I do think so, yes. I don't think that an AI system can solve the same all the same situations where the humans do, but it has complementary strengths, maybe. I mean, imagine all these situations where humans simply are not good. Driving at night is probably a good example. Driving after a stressful day. When you've been awake for 12 hours and it's 2 in the night, there is quite some risk in that. People react. Human drivers react emotional. I mean, think of all these things that happened to you in your last week of driving, which were not really the right thing to do by other traffic participants or by yourself. So there is quite some amount of risk that can be reduced by AI. So of course, there may be things, I mean, currently humans are a lot better in abstraction. So if you see something completely unknown to you before, you might be able to find an abstraction analogy and react based on that. That's more difficult for AI. I'm sure that we make progress there. But yeah, that's there. We need to deal with that. But I think it is compensated by situations already now where AI can simply really be better. I mean, as I said, think of pedestrian detection at night. My personal one of the takeaways from KI-Absicherung is that if pedestrians are not overrun by cars at night, that's because they are on the sidewalk. if they were on the street, they would be overrun, because this, typically they're really difficult to see. Right, and for this topic of unknown things, unseen things, also there is a remark in SOTIF that this is called the unknown unknowns there. So scenarios which are unsafe, but we don't even know that they exist. So the SOTIF idea to address that is to make that space as small as possible, and until we think that the risk is manageable. And also on the AI side, I mean, there are a couple of techniques, as we saw yesterday in Kai-Absicherung, on uncertainty estimation, for instance, which can help to identify when the AI is actually no longer confident about its result, and when it is time to bring the driver back in the loop.
Okay, thank you. I want to now proceed with Armin Koehler. From Bosch. I also have a question here for sure. What are white spots for the scenario description in the context of V&V for AI-based solution in automated vehicles? So, and maybe you also can, spend some few words on the relation to other initiatives more focusing on safety, like Pegasus and also V&V methods and these projects, because we have to bring these things closer together to provide really a good foundation for safety argumentation. Yeah,
thanks. Good question. I think white spot in the relation between scenarios and verification and validation, I think it's pretty much related to, I would say, the billion euro question. I think it was Hanno yesterday asked this. So when are we actually complete? So we want to develop functions, then we derive requirements out of them, but they're not complete at the beginning. We don't know everything because we have to deal with the open world context. Then we derive this in these scenarios, but they're as well not complete. And then now it's our discipline. We want to cover this with data, and they're still not complete. So I think that's the big white spot. So how can we get complete in all these areas in the link between? And you mentioned it. I mean, that's actually the chain of these different projects, and we need to bring them together. So I think each of the projects did a really great job. We have seen it yesterday. I was so impressed about the results from Kai-Absicherung. They brought up so many methods, tools, notations, and the same for us. I mean, we're developing all, I would call it the building blocks, a lot of building blocks that we really can use to answer this question, the annotation. So, I mean, we have seen it yesterday. We can describe ODD. We have the Pegasus model. We can describe taxonomies, ontologies. We have scenario-based testing, all that. We can create variations, all the stuff. I cannot list it, what you have shown yesterday. All. And so there we have all these methods. And on system level, it comes from VV methods. On AI safety level, it comes from you, from the data side. We're caring for this method, but we need to bring them together. And the discipline is to, can we bring it into and that's what I think what is missing, the process, and bring it in an iterative and a structured process to find these gaps and then to close them. And the big question is again, how can we say when this is complete? And I've absolutely have not the answer, but this is really my hope. I think that when we establish such a process, it's a learning cycle that we somewhere come to that during learning in the process. We come to the answer. What is complete? We would not complete, but complete enough to release something. I think that's the goal, because complete can never happen. That's open world context. Yeah, and I think there we should go for. I also maybe I don't know if I can raise a little bit of discussion here, because there I'm thinking a lot about. I wrote in the 2019 paper. Was the white paper Safety First for automated driving. I mean, some years ago, I actually want to ask everybody if there's a new knowledge about that. There was written about this positive risk balance. Yeah, this is definitely, that's the goal that we have to reach. But I'm always thinking of, can we have a calculation, mathematical way to calculate when you all combine these methods at the end, like we are used to. We know it in FTA, for example, for hardware stuff. We have really, there we have the failure rates. We can multiply them. At the end, we come to a number. Do you think that at the end we can get to a number, say, yes, now we have the positive risk balance? And that's, I personally, I don't see it, but it would be very interesting. Raise hands. Okay, you can answer it if we come to that. Because I don't see it, I would rather say we need a process that leads us there. And they're actually, therefore, I actually want to invite you. We invited a colleague of mine, Andreas Albrecht, and he really made a lot of thoughts of that. That would be the next keynote speaker. He will explain that much better than I can about this process. And it's actually a bad news for the engineers. We don't like processes that much. Yes, sorry for that. But I think we have to care for that. And it should be a really helpful process, hopefully, when we derive that, where it's more a learning cycle that really helps us. And we have to do it efficient, I think. And then we again come to the tooling and the methods and stuff like that. And we can all list this stuff like we need traceability. I think that's maybe another very important thing to establish the tools. We need a lot of automation. And then we come all to the stuff what we have heard yesterday. But that's my big message, actually. We need to combine it in this process, hopefully, and to get to that positive risk balance. But can we also bring in the
for sure, but from
the how to calculate this level?
From the perspective of the moderator, I have to ask for discipline, not to change the entire podium discussion. But I think it.
Explain me later on how it works, only to to the others.
But I think it is something we can do it now. So please.
Okay, so I've already proved it that it's not going to work. Okay.
Okay. So I have a second question, but maybe I can come back to you later. Let's proceed with some of the other colleagues now. So and now I want to ask Hardi Hungar. So Hardi, what are the next steps to be taken towards a more virtual V&V? So more taking into account simulation, synthetic environments, and that stuff?
Oh yes, that's a very difficult question. So it has been mentioned I'm from the set-level project. I'm also active in VV Methods. Set-level is about simulation-based engineering and testing. Oh yes, that's about virtual verification and validation, of course. And I must say that producing lots of scenarios and synthetic data, as we've seen today, and certainly also yesterday, Thomas, this is, of course, a great help to that. Though I must say there's a difference between synthetic data and real data. Sure, you all know that. Let's don't forget that. So these are important ingredients to have many data which we can test, but we have to be complete to get at the real positive risk balance. So we need a little bit more than that. Well, if a problem is really difficult, and we cannot fully specify how we would solve it, we have no algorithm from the computer science side. The typical answer of computer science is, and a valid answer is, to throw data at it. Yeah, it's been the same with language translation. There were approaches where people wanted to understand languages, and then from that on, going to translation. Well, didn't work as well. So statistics, many data, many translated text, and poof, computer science succeeded. That's the same way here, that we use many data, but we have to introduce every kind of knowledge we have to structure the data, to enrich the data, to be able to reason about the data. Like we have a grammar, which is of great help in addition to statistics, if we want to translate languages. That is why we need also this kind of abstract labeling, and in the end, a relation between all our data we have and say, abstract ontology capture of the operational design domain where our car should operate. This is a very important thing if we want to do, say, if we want to achieve a positive risk balance. Let's leave that out. Virtual things. This is, we need better simulation, flexible simulation like we've seen in the keynote today, modular simulation technologies where we can put models together on the right level of abstraction, and yes, all of them really working nice and being able to do cloud-based simulation on a large scale. That is to address this huge problem by throwing enough data at it and being able to process all these data with all the help we can get from our nowadays technologies. So, and AI can help in that, both in providing data and also in perhaps steering the analysis process to the interesting spots, because then we get better, faster results on how our car, our simulated car, our component behaves. So these are very important steps, one thing. And now comes the quid pro quo, the difference between synthetic data and real data. And also, yes, we have to know where our simulation is not accurate. We need, say, validity-aware simulation. We need synthetic data about which we know whether they are really usable or perhaps not quite the real thing, where we get just a first impression, a first answer, which we later have to re-evaluate with other means. So this is a very important thing. Know where our approach carries us, and tools and methods which say, okay, here's the limit. From then on, you have to do something which complements these virtual things. Okay, that's part of the answer.
Okay. Yes, thank you, Hardi, for also talking about simulation and the possibilities we have with simulation. I think what we learned in the last projects is that this is an essential tool for many engineering tasks in the V model or whatever you choose to develop systems. And I think
sure,
also
you can't throw so many data at your system for test if you don't simulate it.
Yeah, yeah. So it's really essential. But you also mentioned the topic of real world data, which we also have. I will now come back to you. So because what we see is that we need some real world data for many proposals, but what we also learned so far is that it is not the best idea to just drive around and collect all the data we can get and then see what we can get out of it. Maybe we need a more systematic approach. Maybe you have an opinion on that.
Yeah, definitely. We don't need the lot of data. I mean, it was some time where that was again also buzzword, big data, and everybody impressed us about we need that huge data amount. Still we need it and we need to handle it, but I've also seen from KI-Absicherung, from Intel actually, a good result there. Here's sitting. That they were showing, they looked at the result was, I think, MIOU rated for training of AI, and they challenged with the Kia data having how many 200,000 frames was there, but you have managed to reduce it to 5,000 frames and rated similar or achieved similar results with that low amount of data. So it's always really proof that we need the right data. So and that's when we talked before about yeah, we have this description. We learned it yesterday. We can define scenarios. So then we and hopefully we learn that gaps with the process, what I've mentioned, and then we have an idea what is missing, what we need. And now for synthetic data, I think there we have this automatization you've explained, where we automatically translate the scenario description into production of synthetic data. But how does it work for the real data? I think what we need is, at least in our terms, I don't know if we have the same terms using it. What we need is filters and triggers. We always call it that. So what we consider as a filter is when we search for data, that's when we search in the backend. So in these huge databases, and we want to extract the right ones, that could be these ensembles of AIs or whatever techniques to pick out the right data of these big, huge data stores. And the other one, the triggers, is what is in the car then. So if you drive around and you get something interesting in front of your camera, and then say, okay, this I want to record. And that could be actually, that's what we call the triggers. And could be anything, could be very simple, like think about A/B function that we have already in series. If the A/B triggers wrongly and then the driver pressed the gas pedal, so it was obviously a false positive, so because it was overruled. So as a simple filter, don't need AI, then you trigger it and you have interesting new data again. Mm-hmm. But could also be AI, of course, and it depends on the storage in the cards that we have, how big these we can also do ensembles there when we have the calculation power. But yeah, I think that's the answer. These two things, that's what would be my answer. Triggers and filters we need to establish in combination to this process.
Yeah. And in particular, it's not just a thing of big data. We need to have the right data, which helps us. So it was always in so many projects. The guys are working on large and big data sets, and they had the idea just to throw some algorithms out of the database.
More is better, but not always.
And then everything works well. So it was never the case. So I think it needs more a systematic approach. So and thank you for commenting on that. That was great. So but now let's go more to the AI-based function. So Gerhard Schunk from Valeo. So in particular for AI-based functions, we see we have at least iterated processes how to improve the AI over the entire life cycle. And we are also discussing in the systems development more and more these DevOps approaches. Maybe you can talk a little bit about this topic.
Yes, thank you for the question. Good. I mean, development operations, when I think about it, I think continuous integration, continuous deployment is really a key feature here. And I think, I mean, here we could also maybe look at all these big internet tech companies like Google and Amazon. I mean, yesterday a colleague, for example, told me that like Amazon has 10,000 deployments per day, actually. And but I mean, the problem is, I mean, we're not running YouTube, so we are running automated cars. So it's a completely different business and completely different issues, I think. I mean, one problem we are facing here is many OEMs, they also want to have their releases tested in a car before they can send their fleet out, like 30 cars, and do the huge recording cars here, and which is really costly. So we have to be, I think, a lot more careful before we deploy. So I think it's really kind of a dream to look at this continuous deployment every day or so, because we need this real testing. And yeah, so I think one solution maybe to that problem is that we go more and more into the integration of hill testing into like this continuous integration domain, that we maybe also run our hill stations. For example, you can imagine maybe just a camera looking at a screen and run them like overnight and do some real hill tests. But still, this brings us the problem that it's not the real world. It's still not like the real cars on the road. It's not a field operation test. So we kind of struggle here more. And here, I think exactly at this point, I also feel that KI data tooling comes into play, because I mean, you can test a lot with like the simulated data. When I see like this Nvidia talk, they showed us like millions of frames, basically. Also here in K data tooling, we already have, I think, 300,000 frames. You can run them basically maybe every night for testing. But maybe if I look into the future, maybe a development which is still like coming up is going more to from this open loop testing, where you only like feed the camera images into your AI system, get maybe some confusion metrics with some results, but go more into like this closed loop testing, where you can also like test the reaction of your car. And I think this is really essential because, I mean, this closed loop testing, I mean, so far you only do it on the road, like with field operation tests. But if a simulation could take this over at some point, I think, yeah, I think this could be a big step towards development operations. And yeah.
Mm. And then, as you mentioned, it is not just a question to have one test facility. You have to integrate really different test facilities, and this is also, I think, a challenge for the future. In particular, when you think about iterated development procedures, because then you have to have them in place, and you have to have them in operation very easily. That's really a challenge, I think.
Yes, I think so too, yeah. I think it's also a cost and a time argument. I mean, if you see that, I mean, the problem is that the common driver is just so amazingly good that the usual driver, I think, what's the number again, produces only one accident with like injuries every 10 million kilometers on a highway, I think, in Germany. And so you cannot cover such a test. You cannot cover it with like your usual testing fleet. I mean, this would be insanely expensive. And if you think about you doing a next software release, then you have to run your whole fleet again. And they run hundreds of millions of kilometers until you have the statistical proof. Even the 12 million kilometers do not suffice. You need more for statistical proof. And so this is, I think, a huge argument to go more into this like SIL testing and K data tooling. Mm. Yeah.
Okay, thank you. So I want to proceed with Christoph Schiller. Christoph, it's great to have you here because as many of us know, you were already working on many of these topics while others barely know that these topics are existent, for instance, me. So it's good to have you here. And what we see is when we talk about intelligent systems and that stuff, we see often that communication and the cooperation is essential because none of these single entities is perfect, but sometimes it's relying on cooperation, which makes and guarantees a more safe operation. Maybe you can talk about a little bit about the role of communication, cooperation as a feature of intelligent systems.
Okay, thanks for the question. First of all, I want to give one thing on one conviction that I have on AI is that AI systems will drive much safer than humans can in the very near future, and not in the sense of completeness, but in the sense of sufficient completeness. I mean, our biological intelligent systems are neither complete, so we do accidents, and the question is not, are we able to build zero accidents, then we'll never deploy automated vehicles, but the question is, when are we so safe that we societally will not only say we allow such vehicles on the road, but when we even say we have to have those vehicles on the road because we cannot afford humans killing people while driving cars, so we need some technology which prevents that, and we'll have that, and we should deploy it when it's there. We're not yet at that point. Not to your question as well. But yet communication is very important in driving. Think about when you drive yourself. You communicate all the time. We recognized that when we did the Benz drive in 2030. Many people wanted to communicate with our safety driver, who didn't even know what the vehicle was planning. So in the end, we developed a strategy: don't look at anybody, look straight, like a very, very unfriendly, wired driver. Because people who looked at our safety driver expected then that they made an agreement. Yeah, that the safety driver, if you smiled at them, would let them pass first, and he didn't know whether Berger would let the pedestrian pass first or not. We recognize the lack of communication. Communication is extremely important, but the most type of communication that we do while we're driving is not through gestures. It's through our trajectories. So we communicate while driving with our trajectories. Think of when you're driving highway, you open a gap or you close a gap, which is a clear sign to anybody who wants to make a merge-in maneuver, that you allow that or that you don't like that at all, or we nose in. All those things are not part of the maneuver. It's not meant for having a smooth transition to another lane, but it's communication. So we do a lot of communication, and I'm absolutely convinced that communication among vehicles is as important for automated vehicles as it is for manually driven vehicles, and of course also in mixed traffic, which we'll have for a long time. And I'm happy to see people like Konrad Doll here, who are in the cooperative interacting automobile project with us and do research on that. And of course, automated vehicles have much more capabilities to communicate. Like we have the chance to communicate in milliseconds via radio transmission. And that's, of course, something that humans can't do. Humans have difficulties to communicate. We need long times to understand what are others thinking. Sometimes we have misunderstandings. All these things can be significantly reduced when you do radio communication. And we need a language for that. We need to understand the language of humans, which we can do from trajectories. Well, there we need real trajectories, real data, not simulated data if you want to investigate how do humans communicate in traffic. And we need to have ideas on what to communicate and how to communicate among automated vehicles, and that will make them much safer. And so I believe that automated vehicles will not be in the market before that is really addressed.
Mm-hmm. Thank you also for your general comment at the beginning of your statement, because I also see that AI will drive much safer in the future. We need to discuss this more on the system level, not just on the vehicle level in all the different situations we have today, because I think we will also have some adaptation of the overall traffic system, which also are necessary to be successful introducing AI-based systems in the traffic system. Thank you for your contribution here. And I would like to proceed with André Rolfsmeier, so now from dSpace. And I also want to stress again the topic of the different fields of action when we see how do we come to a sufficient tool chain, which helps us really to not just put the light on some spots, but also be helpful to come up with the entire argumentation and safety argumentation. Maybe you can talk a little bit about this topic.
Yeah, thanks for this question. Exactly what we are currently doing. So we are currently developing with customers an entire V&V tool chain to validate actually the entire AD stack, or the automated driving system. And the big challenge here is that the customer starts thinking about how to bring this into the cloud so that we have a consistent CI, CD, and CT process in the cloud. And here we are working with the customer and typically also the cloud supplier. So an Amazon or a Microsoft, or in China it's getting a little bit more tricky then. But this is currently the challenge we have, and we have already a couple of projects where we are developing this entire V&V process with different test stages. So test stages, real test drives. We have then the data. Then we have how to process the data, and to set up kind of automated pipeline. So I mean, when you have to process the data, I mean, when you have a CI/CD pipeline in the cloud, you expect high iteration cycles there. So it cannot be that it takes months or even longer to go through the entire cycle. So we are working on automated pipelines. Take the data, process the data, anonymize the data or annotate the data and feed this data back into the other test stages like data replay testing or reprocessing, what we have heard also from Nvidia today. And the big challenge is also how to combine now the data-driven pipeline with a simulation pipeline. And that's also what we are working on. So, and I think also here in this project, having in the end a kind of pipeline by means of which you can take the data and convert it also in a kind of simulation context, so that you have then the same scenario in the simulation world, and then you can, of course, change the simulation scenario according to your needs. What is a big issue at the moment is you need a kind of more systematic approach than currently. So actually we have to think from the ODD. So what is the ODD for what is the test goal? And the test goal in the end describes what test stages I need: data replay, real test drives, hill testing, sill testing, etc. And we need a kind of systematic approach in terms of from the ODD derive what scenarios do I need to test, what is the test specification, what are the actual tests, what can be tested in the real world, what should have to be tested in with hill stages or sill stages. So this is one big challenge. We are working on this, and here in this context also the standardization makes progress. So ASAM has taken up this. Another thing that also has been taken up by ASAM is having a kind of standard in terms of how to describe labels. So when we create such a kind of pipeline, converting real data into simulation world, of course we always have to write import filters again and again, because everybody captures the data in an individual form at the moment, so and labels the data in a certain individual form. So we need also work on standardization here. And one big issue we are working on, it's not directly related to AI, but it's currently one of the most important things we see from our customers is software-defined vehicles, and how to virtualize these complex things. And then, of course, software-defined vehicles contain also the different domains: ADAS-AD, infotainment, drivetrain, connectivity. And this is a very, very hot topic. We are discussing how to virtualize the software-defined vehicle, how to bring this in the cloud, how to set up these kinds of fast iteration cycles.
Okay, thank you for sharing your thoughts with us on this topic. So, but because of the time, so I now want to come back to Robert Bruckmeier. So yeah, you have to still work here.
That's fine.
So I think it was great to see also from Christoph that he believes AI plays an important role in our traffic system in the future. And also a question to you: what from your perspective will be the first functions we will see where AI plays an important role? Not just talking about automated vehicles, but let's say talk about advanced vehicles. What are some ideas you have where these functions can be implemented?
Yeah, thanks for the question. So let me nevertheless start with automated driving and just share the conviction that automated driving will be big. And let me share two examples. I lived in China, and once I was in a taxi where the taxi driver was falling asleep while driving. So I would have so much wished to be in an automated vehicle, right? Example one. Example two, in big cities, people live typically in compounds, huge high-rises. There's always a reception 24 hours, and a way to handle decongestion is to deliver all these packages during nighttime when the roads are empty, because they are dumped at this the reception anyway, right? Why not do that at nighttime with automated vehicles? So I think these are just two examples on automated driving, and I think as we are here, we will solve that problem, make great products, and they will help us, right? As consumers, they will help us as society, because we are taking care of making them safe, right? But then there's much more than automated driving. Just think of the driving experience. We talked about communication, right? You don't have, you don't want to look at your screen to communicate with your car. You want to use language. Language has made a huge improvement with AI. And so I think there will be a big progress because AI will understand the context that you're in your driving situation, in your personal needs, in your communication. And this will be personalized if you want it, right? And I'm convinced that at some point people will want that because it will just make a so much better experience. And then, taking this from the product to the process side, AI is helping to really understand the meaning of text. Now, many of our partners will know that our specs are lengthy and sometimes difficult to understand, and AI will help to focus on the meaning. You can search for some topic, and you don't need to hit the wording. It's about meaning, right? And we are close to that point, and we can check, are the specs consistent? And so this will help in a big way. And of course, there is production quality, and we are rolling out AI-based quality systems like visual inspection in a big time globally. So this is happening, and I'm fully convinced that we will have like these 15% of AI impact on the world economy, on everyone's lives in 8 years, right? It's not far. Yeah. So I'm bullish about AI, and thanks for being here. Stay hungry, keep learning. That would be my advice.
Okay, thank you. So that was really great to have also these statements, because it's really some motivation for all of us working in this area. So, but now I want to do one last very, very quick round. So each of you now has 30 seconds, and let's imagine we did some time traveling. And let's assume that we are now 5 years in the future. So this is now the time we are. And what do we have achieved in the area of AI for safety critical applications in context of automated driving compared to 2022? So who wants to start? You want to start? Let's go from the right side to the left side.
Then I start. I mean, I think me, similar to maybe hopefully all of you, I kind of believe in AI. I think it's a quite interesting time to work in AI. I mean, we only have a very few products with AI in our cars, and so it's really will explode, I think, the next upcoming years. So maybe if I may end with a personal note. So I have a 2-year-old son, and I actually bought some AI ETF shares for him, because I really think this will, maybe in 20 years, who knows, it will be worth it.
Okay, that's a statement.
Well, I'm from the verification and validation world, so and if it was my younger self standing here, you would probably hear something optimistic about 5 years prospect for verification validation in terms of, say, proving the positive risk balance. Now I'm a little bit older, and I'd say we'll have some pragmatics, and lots of tools and lots of methods. But it will be a vast landscape with some nice high peaks, but also deep down below some valleys of unreasonable methods applied with not validated tools. So I do hope for some, limitation-aware tools and methods, and this problem will be attacked, but it will not be solved as it would have to be for a sound method within the next 5 years. But I hope to live 5 more years to see whether my prediction comes true.
But yeah. Let's quickly proceed with the round. So please,
I talked about products and processes 2 minutes ago. Let me take one more thing. Innovation is done by humans, right? By you. And I think in 5 years, the team here will be a lot bigger, right? Because AI will be growing. So please find your friends, bring them on board, educate them. And I think that is also going to be a big change in the next 5 years.
Okay, thank you. Proceed.
I think in 5 years we won't have one big step. One great thing that is there, like out of the box, the ex machina or something, but we will see a gradual increasement of autonomy. And I'm sure that there will be elements that rely on machine learning and that are safety relevant. We don't need to wait 5 years for that. But it'll be small things, yeah, things where we really say the risk is manageable. We have everything. Yeah.
Okay, thank you.
Well, I would say we already have AI now in the vehicles, in the ADAS lower levels, 1, 2. The change maybe will be that I expect that we have significant number of cars on level 3 that gives a higher expectation on the safety actually, and therefore I repeat it. I think we will have this. We will have to have this process running where we really can argue that the things are safe and that they then all really safe, and that hopefully, yeah, we have no fatal accidents on German roads there. And at the end, it's also for us important that all developers actually can sleep well. We think it's very important that even if something happens, there's a residual risk, but then we can say we did everything and we can sleep well. Yeah. That's important.
Okay, my prediction is we'll see evolutionary improvements on cars, like having level 3 plus functions in cars, which starts this year in one German car even, and that will get more and more function and more competitors internationally, and we'll have a disruptive introduction in the next 5 years, definitely, of things like last mile city taxis. I very much hope that in both areas, German manufacturers and German universities play a major role.
Yeah, what do I see in 5 years? I think in 5 years we must have a kind of process, methodology established, also approved by the authorities like TÜVs, so that we can really validate the trustworthiness of our pipelines, simulation pipelines, and also by means of simulation and generation of synthetic data, etc. Another thing is, I strongly believe that it will be possible to systematically analyze the robustness of AI. At least that's why, for example, dSpace invested here in a Berlin startup, Neurocat, who is investigating this. And I think it takes some time to have here really a kind of I don't know, mathematical argumentation or a kind of plausible argumentation also towards the authorities, how to, statements about the robustness of the AI. So I'm not quite sure to what degree we will be in 5 years, but first stages will be there. I'm quite confident.
Okay, thank you. So it really was a pleasure to have you all here on stage. I hope it was informative for you as the audience, and then also I hope it was a little bit fun for you too, to listen to us. So yeah, thank you. Then we close this session here.
This vast number, this open context with infinite number of possible constellations. It's much more comfortable to take a machine learning model and train it on some labeled data set. So, and with this, we can make use of this generalizability capabilities of the model and have a much more broad coverage maybe than in our training data set. However, with this, a completely new kind of development arises. Formerly, we just looked at requirements for the functional specification, and now we have to look at the data specification as well. And new safety risks or safety concerns arise that also now concerns the data coverage, the distribution, corner cases, and so on. And this brings us to the new role of data in machine learning. I would like to take this very abstract picture to just show these different deviations. Let's assume this green box down below is a generally accepted concept that we want to learn with our model. And let's assume this large green bubble is a data space that needs to be covered to get this training result. But we have a residual risk that we have to accept to make this an ending or a kind of discrete space that we can limit. Without this residual risk acceptance threshold, let's say, we cannot do this. But still, if we come to this dashed green circle, this might be the current knowledge on our understanding of this ODD. So our concept that we initially know about is deviating from the true, let's say, real part that we need to cover, and this need to be approximated step by step. If we want to do a machine learning solution for this, we would collect data, and let's take this violet bubble as the available data set that we have covered, or the data pool. But we might still not be able to learn this. Our machine learning model has maybe some limitations, some limited learning capacity, so it can maybe just cover this dashed blue part, this dashed blue line, yeah? And still, we might not have this as a final result because we have a limited number of optimization cycles. We may end up in some local optimum where the optimizer is caught. So this violet filled out part is maybe then our actual result. And there's lots of sources for deviations, and this cannot be brought together in one step. We need to do this iteratively. Try to bring these bubbles together. And this is, in the end, the goal and motivation why we need to understand the data contents and the effect on our models. To give you a very simple example how we could, let's say, what kind of gaps could look like in data sets. I've brought a little analysis of the Bosch traffic light data set. This is a very small typical traffic light data set, public, open source, recorded in US. And here on the left side, you see all the bounding box centers of the traffic light housings on the imager plane. They are in the upper half because they were all recorded when approaching the traffic light on flat ground. But what happens if you want to go over a hill? It's very steep, and the traffic light is unfortunately directly behind that. Then this traffic light would appear in the lower half of the image plane, and maybe that was not really covered by the training part, and it could be possible that it's overlooked. Or at least we should test it and not forget it. Maybe a much more serious part is if we analyze or if we display this distribution over the different bounding box housing sizes, which is an indirect distance measure, let's say separated by the color states, then we would have this right picture. And here the small traffic lights are very far away, the very large ones are close. And here there's a very obvious other gap. We don't have any large traffic lights here. So if you want to use that data set or reuse it for Germany, you would end up in overlooking traffic lights because they are at the closer end of the intersection. In US, they are always at the far end and appear much smaller. So such gaps are, of course, just a very small example of the overall possibilities. They need to be iteratively identified and closed. So let's look at the machine learning lifecycle. First of all, we have a problem space definition. As we've seen before, this is not the true one at the beginning. This is just a part of it. And we need to also iteratively refine this. Then we start maybe from scratch, collect data from zero, and separate it into training and verification data. Then we define a model. We can maybe change it later. We define hyperparameters, the architecture, the cost functions, and our optimization strategy, and train the model on the training data set, validating it against the training validation set, for instance, and then verify again against some test set where we can use KPIs of different performance measures to see if the performance is okay. But then we will certainly have troubles and have to iterate multiple times, optimizing our cost function hyperparameters until we are satisfied. But then we need to test again on the semantic level. And here comes in the broad tests where we look for data coverage. We need to, let's say, cover the whole ODD as we know it as good as possible. And if there's something missing, we can iterate in this inner data loop. If we're then happy, all tests have passed, we deploy the solution. But is this the end? Certainly not. We have to monitor this solution. We will not do this in one iteration. We will have multiple corner cases, the unknown unknowns that will suddenly appear, and we have to evaluate them, make a risk analysis, make a safety analysis, and see, do we have to consider this? And if yes, we have to iterate again. And this would be done in this outer DDE loop. This is triggering the process again. Now let's formalize this, and therefore we cannot only take the perception function into account, we need to look at the whole system, even maybe at other vehicles included. And here on the first level, this is called DDE 0 in our model. This is a vehicle level where we look at the vehicle from outside and at an overall point of view. Here we can define the use cases and the scenarios. Then we define a sensor set and break down this field of views, and we can use multiple or multi-sensor data sets here to evaluate our functional chains. Then we break down the functional chains into different components. Each component has its own data domain, and on the level DD2, we can look at those, looking at single sensor data, frames or sequences. That's mainly for testing. Similarly, on level 3, we do the same for the training. But here we also have the data pool implementation, not only the model, but also the pool, where we consolidate all the data needs from the levels above and collect iteratively new data. Then we can display this on a rather bird's eye view level, on how this iteration would work. We start always with a mission definition, drive from A to B, very simply. At the beginning, maybe without any curves and so on. Then we derive use case, different use cases, like handling intersection, drive, follow the lane, or something like that. And each of these use cases will be broken down systematically into base scenario classes. Each base scenario class can itself be varied and broken down into scenario collections. This would be, you can simulate this directly, right? But you can also derive from each of these classes data requirements for each functional chain, for each component, down to the model. And this is then the entry point to our process model. In the simplest case, you define what kind of color states do I have to identify. In Germany, red, green, yellow, red, yellow, nothing. And in Japan, suddenly it's blue. You know, this is such kind of criteria, but also it could be going down to the feature space level. And then we iterate through the different levels, and it's probably pretty, we can display this in a simple mini V. This is a sub-process for the implementation and verification of a data set. This is for the development data set. We start with requirements. At the first block, this could be simply what kind of color states do I have to cover, what kind of box ratios, and how many of each of these classes. We break it down to the what. What kind of scenarios do I need? And this is the data set design. But this is not, again, the requirements. This can be a set of filter configurations. This can be a set of simulation configurations, close to code. And then we drive filters with it to look for real data that we take from the pools, and we do it in a kind of rainflow counting. We always work with classes here and associate the different samples we find to the classes. Then we verify the statistics, which we automatically get against the requirements. We can do the same for testing, but we have to do that with different data pools, one for training, one for testing, to be independent here. All right, I have to accelerate a bit. So if you stack multiple of these mini Vs, for each level you get this data V, which breaks down the requirements from the top level down to the data pool and goes back to the verification part. This goes in parallel with the system development process, and both are coupled with the data sets. And this split is important because we want to take complexity out of the requirements. We want to have generic system and software requirements that apply to all scenarios, and all the data part is handled in the data V. And then we are able to quickly change ODD without touching the rest. And this allows us quicker iterations if we have such an ODD shift. So this has been associated with the KI-Absicherung test strategy. We have associated the different methods to the blocks. I will go quicker over it. And then I would like to just pick 2 examples of methods which can easily be applied in the process, especially for the requirements engineering part. This is the combinatorial testing. You can use it for all system levels. You can use it for scenario specification down to, let's say, object level specification. And you can reduce the complexity by making use of this scaling. Just do the single parameters first and then do pairwise if you have more data, then triple-wise and so on. And of course, the correlation between the actual performance of a DNN and the data coverage, that is tested here in the search-based testing part. And you can generate new requirements for weak spots, examples for for simulation, but also for filtering. You can directly use this as an input for the filters. And actually, an active learning cycle does nothing different. And this would be then the final slide. And my big picture for the next future, we will not use only real data. We will not use only simulation. We need to bring this together where it fits best. And this gives us a mixed coverage. And the overlapping area we need to use to evaluate the current appearance gap of simulated data against the real data. We need to systematically do experiments for training. What effect does it have if I change portions of the data set with simulated data? And even if I only use it for testing, it's valuable. We should not drop simulation, because when we do the iterative, if we combine this process with an iterative safety argumentation, we will talk about very, very concrete scenarios which we break down. And Murphy's law says if we want to have certain real data for this, we will never get it. We can run millions of vehicles, but this one we don't get what we currently need. So we just replace it, even if it's just temporarily, with simulated data, and this is better than doing nothing. And if we later on find real samples and see, okay, this was not 100% correct, we can do another iteration and replace it, or keep both if it works, and we have better coverage. And this is, in the end, a necessity in my eyes to bring this together, and this should also motivate this project. Here you have the chance to do these experiments, to try this out, and let's say bring further solutions into the system development, software development, machine learning development, which we could easily integrate into the process. Now I have seen the red flag. I'm done. Thank you very much. Maybe it was a bit too much, but I think I could transport the basic ideas.
Thank you very much, Andreas. I think it was great to have one more now structured framework where to put the different data-related tasks, and also thank you very much for the additional instigation. We're going to have a question. I think you're going to be here.
You can ask me. Yeah.
We're going to have a question and answer block for the whole presentations also in the afternoon. But maybe if we really have one urgent question that we of course will take time for. If that is not the case at the moment, then I would now come up with a way of how to collect the questions. Thank you very much, Andreas.
Welcome.
We have actually prepared a small tool, and now not only for this morning, but I would encourage you also to use the tool throughout the day to submit questions that you would like to see answered. Maybe answered by the presenters in the afternoon, specifically for the content that we have for the day-to-day. but also, of course, ask questions that guide us further. It's a midterm event, and as I said initially, we'd like to get as much instigation and input from you of where the project should be steered in the second half. And we already discussed yesterday that there's probably going to be follow-up activities as well. So also, please ask questions that you think would take us beyond the horizon of the immediate project that we're talking about today. We'll try to answer and get back to them in a panel then in the afternoon. We'll be bringing back the QR code throughout the day in case you don't catch it or didn't catch it now. Now, it's time to move on, and I'd like to welcome Evren on board. Evren will be talking about yet one more loop picture, which is now the data flow lead image that we are following inside the project of KI Data Tooling. Evren, floor is yours. Thanks for being here.
All right, thanks. Yeah, sound is on. Okay, cool. All right, well then I'll get on with my part. So introduction in terms of course, in the project itself, we have a certain workflow, how we work, right? And just this button probably, yeah. And that workflow, I want to kind of draw like the big picture now, what the steps or the building blocks within that workflow are, so you have a better understanding of the talks that will follow in the afternoon actually, concerning the topics itself. So, of course, initially, what is the scope of KI Data Tooling itself, and why is this important? I think we heard a lot already about that in the last talk, so I don't want to go too deep into that. It's just a couple of slides. And then dive into this workflow itself. So, KI Data Tooling, we know, well, complete data solution. What does it mean? Well, how do we train and validate AI-based automated driving functionalities in the future? How can we support and build some kind of a blueprint, so to say, for the future, that these functions can be developed without always inventing the wheel from scratch? That's very simply summed up. So, of course, you have your training, you have your test and validation, you have your operation afterwards. Is also something that we've already seen. But the question is always, what kind of data do I actually need? What kind of data do I actually have? And to train my model and to make sure that I really get the result at the end that I need. And this is where the synthetic data comes into play, so to say, because if we look at, let's say, classic approach, right? Just real data, I'll drive around, I collect the data. There are certain scenarios which are very common, where I have a lot of data, or a lot of quantitative data, so to say. But on the other hand, I have a lot of exceptional situations which rarely happen, which we also already talked about in the prior talks. So here the idea is to close this gap, this, let's say, this data space, by adding the synthetic data, right? Because you need a lot of kilometers to drive around to cover even at least the slightest bit of what's really necessary, and to reduce the effort here and to also close this gap of the data space. Synthetic data is, in our opinion, a good solution. So by taking this synthetic data into the game, you can have like digital twin topics, and also cover corner cases which are maybe difficult to cover in real data, and so on and so forth. Again, don't want to go too deep into it, but this is just depicting what the main idea is. So what does it mean for us now? What is our workflow, right? So workflow here again, please just bear in mind that this is really the workflow that we are working, how we are working in KI Data Tooling. This is not meant to be the outcome. This is the working mode within the project itself. So the difference will be seen here in this evaluation part, right? So at the end, evaluation, not validation. I'll come to that later, but let's start from the left to make it easier. So what are requirements? Well, that's obvious. If I want to train something, if I want to produce something at the end, whether it's training or whatever, I need requirements, and the same counts for data, right? If I want to train a certain AD function database, then I have to know what kind of data do I need. So this is the first part here. Afterwards, if I know what kind of data I need, I want to produce that data. So that is the second step here. Again, we will have a look at it later, where we talk about synthetic and real data and so forth. Then the storage part, although storage always sounds so simple, like just put it somewhere it's stored, of course this is way bigger than that, because if you have data like that, we had already mentioned for real data, it's quite important if you have constraints, like legal constraints and so on, but you have data governance, you have accessibility, the provisioning of the data, you have the discoverability and so on. I'll talk about that a bit later on. So just to make sure here, storage is not just, I put it somewhere, done. Enrichment, well, I have data, that's great, but I have to prepare it for the actual AI function. So that's the enrichment step, which is, I think, a very important step, obviously. I think I don't have to explain that to anybody. And, well, the goal eventually is, of course, the training itself, so shouldn't be missed here. And last but not least, again, here, the evaluation part. Why evaluation, not validation in this workflow? Well, what we're doing is we're not developing AD functions in the project, but what we are developing is actually, like I said, like a blueprint how AD functions could or should be developed in the future. Hence, we want to not validate per se, but we want to evaluate the concepts and the methods that we've derived within the project. And that's why we have here a back loop pretty much to all of the building blocks, because depending on the outcome, we will see what part of our workflow here has to be improved. Alrighty. So let's go step by step through these building blocks. Again, just shallow overview, right? Because the talks later will go into more detail. First step, we said requirements. So of course the question is always, what is actually the function that I want to train? And if I know that, then I can maybe decide what kind of data I do need. Though this will, just to use the word again, not be a complete answer, but at least a certain requirement will be established here, and the point here is to have a definition that is as standardized as possible, so I can have a common understanding on this, because we don't want to have of course, just my project, I do my stuff, but to have here a common suggestion what could be good to define actually requirements, certain suggestion for a common standardization here in a ticketing system, which is then used as an input for the production of the data. And what is the production of the data? Well, producing data can be, multiple things. So first of all, we talked, like I said already, quite a lot about synthetic data, real data, and so on. But also the topic of this augmented data is interesting, which is kind of like a mix of different data sets. So it could be real with synthetic, whatever. That's a third pillar here. And the fourth pillar, infrastructural data, is also an important question or important set of data that's necessary here. Because, of course, if you're in the car, you have LiDAR, radar, camera, and so on and so forth. But what's happening around? So just, I don't know, like weather, road conditions, stuff like that, right? This is also necessary. But not just think in the context of real data, but also think in the context of synthetic data. It becomes important. What kind of assets have I used actually? So what are the textures? What are the models, and so on? So this is really like a full coverage of the data, not just the data that I produce, but actually what have I used to get to that data itself. And from here, of course, if you produce data, well, you got to put it somewhere. And here, the important part is, in our opinion, that you have some kind of a common place, first of all. Common not in terms of, well, not old school common. We got one hard drive and we put it on that one. But that there is a provisioning that allows you to access the data as easily as possible. And as easily as possible, usually, and in this case, in our opinion, also includes, of course, the definition of the data itself. So what does the data look like in terms of structure, formats, the content of the data itself, so that I can easily use data without always having the problem of transforming it, or transforming is actually already the next step, because before that I have to understand the data, right? And that is usually a big issue when you want to reuse data, that you can hardly understand what someone has recorded somewhere and put somewhere. And so the goal here is really to find a common definition to ease the reusability as good as possible, which brings us to the cataloging part here, because that's what Armin mentioned, right? The filtering, for example. I have a lot of data, but and not just my data, it's data of huge group or whatever, but maybe I just need just a couple of frames. Well, couple is maybe, of course, let's say thousands of frames, but not 100,000 of frames, right? So I need a certain set of frames for my training. So how do I find that set as easily as possible again here to really train my model without using unnecessary data, so to say. So this focusing on the actual necessary data for your AI training rather than doing this, let's shoot for everything and see what happens. And a big part here also, maybe don't misunderstand this, that it's just on the side, but data management, of course, is a huge topic, which includes pretty much everything that has to do with data governance, the legal part, and the versioning, and traceability. So how do I actually get, where does the data come from? How does it end up in some kind of a model and so on? This full understanding is also important for, well, if you develop a critical AI function, you have to at some point really go through an auditing. You have to really explain why you think this stuff is actually working, right? So in classic software engineering, you have that kind of auditing too. Where is my code? How did it develop and so on and evolve? And pretty much the same counts also for data. That's an important part. Usually, well, not usually, but in some innovation projects, you have to just a set of data. You run something, you say, okay, cool, works on my machine. But here we have to really get out of this works on my machine mentality. And there, this traceability and full understanding of the development process is, of course, very important. Now that we have the data, we have to, well, prepare it for the actual AI step. And here, just to mention a couple of points. So context data is, like I said, this, in our case, the metadata, so to say, on road conditions, weather, and pretty much everything that, well, explains the context of the actual recording. And labeling here is an interesting point because, of course, depending on the source that you have, this labeling becomes rather less or more complex. Right? Real data is, of course, a different scenario than synthetic data. And compression is, yet again, also a very important point because we've seen the numbers from Nvidia. That is quite a lot of data. And you have to have some kind of a good solution to get, a handle on that stuff. And not last, but of course, pretty last, so to say, the training itself, right? What is the task here? So everybody knows what AI, what training means, but in this scenario, the interesting part is that we want to combine the synthetic data, the real data, and the augmented data, and so on into a training. But for that, you have to have some kind of a understanding what effect that synthetic data, for example, has on your training. So is it comparable to my real data? Am I causing any issues and so on? How close is actually the synthetic data to my real data? And derive maybe new requirements, which kind of loops back, right? You see in your training, okay, this somehow was not sufficient. I need more data. And this combination is kind of the tricky part, so to say, to make sure that we don't cause more pain than gain. That's to put it very simple. And which brings us to the evaluation part. I'm a bit rushing, maybe I'm even quite too fast, I don't know. I have no pacemaker, but I'm fine, okay. Evaluation part, well, the evaluation part, like I mentioned already, is, well, we want to know what is the quality of the outcome here, of the whole process that we're trying to suggest here. So one interesting topic is this digital twin here, concerning, well, you can have two ways, maybe more, but here the focus is on two ways how you can kind of compare. First, of course, the prediction comparison. So I have used synthetic data, I haven't used, so how does the result actually compare? Is the model still working as intended? And am I close to the real one, better, worse, whatever? That's one part. That's kind of like this post-mortem, so to say. And image distance metrics is kind of like the other way around. So upfront, I can check. So, okay, with a digital twin, I have, well, seamlessly similar images of a road and the cars and so on. I'll really check, okay, are these images close to each other, whatever the metrics there is. And that is part then of this building block to define here metrics, is to understand how I can define the metrics of the closeness of the images from a synthetic generator or the real recording itself. And I think this is mainly also interesting because, of course, again, here to make the difference to the actual AI development, this part, if we answer this part here, this won't be the big question, at least maybe still a question, of course, but not the big question anymore, because here we're trying already to answer the question whether synthetic data is comparable and how it is comparable to the real data set and how it can actually be used as a, let's call it an additive to the real data, because I think it's not completely going to substitute it, but definitely add value to it. And yeah, which kind of then, like I said, loops back then to different building blocks to improve methodology and concepts that we've developed within the Kai data tooling itself. That's pretty much already it, big picture-wise. Of course, the topics itself are way more interesting than the slides that I've just showed you, but that will come then in the afternoon. Hand over to you again.
Thanks for the overview, Evren.
You're welcome.
It was a great look, a great picture look at the radar screen that we're going to go much deeper on in the individual building blocks and presentations in the afternoon. We are heading for the lunch break very hard now, but I just wanted to say grab a bit to eat, of course, but also don't forget that we prepared and also already opened the poster session in the other room. So there already is quite a chance now during lunch to take a much more deeper look at the individual technological developments and achievements that the project has developed in the past couple of months on each of these steps that Evren just showed. Exciting posters being prepared, so you'll have a first chance during the lunch break, and we'll be back together at 12:50 for the next session and for the deep dives in the afternoon. So enjoy your lunch and enjoy the posters. Be back at 12:50. Thank you. Great. I think most of you made it safely back from lunch, which is great. I hope you enjoyed the food. Great hospitality here by the Volkswagen Group. I really need to hand out a big hand of applause and compliments, and hopefully Stefan Scholz will be able to take it back home. Was really a great opportunity to have the two events co-located and hosted here. We're going to continue now with hopefully some of the impressions that you brought from your discussion on the posters and bilaterally from lunch. But we'd of course also like to guide it a little bit with our workflow model that you just saw presented by Evren a couple of minutes earlier. We're going to go deeper into requirements and production, enrichment, training, evaluation, all the storage and data management, of course, as well. And the first two presentation slots will be by Armin Koehler, whom you already know, and by Marcel, who is an engineer in the data center activities at Valeo. And I just already introduced you, Marcel, because I think you're going to be handing over more or less seamlessly between the presentations. So all yours. Enjoy your floor.
Thank you. Okay, let's start with first workflow element, the requirements. When we talk about requirements for AI-based development, I want to give you two perspectives, actually. As a motivation, so what do we have to consider when we do requirements or data requirements in the industry. And that's I want to elaborate a little bit more about what kind of data needs do we have there and what are production options actually. And this for motivation, because what we do here in the project, that's then the second perspective of AI data tooling, we do method development. So it's a bit different when we talk about what requirements on data is. And here I want to elaborate about our production process that we have set up to solve that. Yeah, looking at the industrial perspective, maybe it's a bit a summary of what Andreas in the keynote has told, maybe bit different perspective or summary. When we talk about data-driven development, we have to rethink a little bit how we develop. All we know that classical development process that goes along the Venn diagram, very simply here shown, where we start with requirements. Typically, we write them down in doors. They're explicitly given. At the beginning of the project, we normally were really able to write them down and transfer it to design and then into implementation. So we code it and then we just test it, have one-to-one representation often, and we can trace that. When we talk about data-driven development, that goes a bit different, I think. We more have to think in relation to in a loop. Yeah? We still have a function goal that we have to develop, but the requirements are implicitly given, so we cannot explicitly note them down. As you've seen in Andreas' keynote, we also don't know all of them, so we have to describe a little bit with use cases, also that have we learned yesterday with the ODD, with scenarios, and that then we translate into data sets. First of all, of course, the training data set, then we train the model, and here we have already the first internal loop. We check the performance. Yeah? That's seen here below. Second is then the test data set, and with that we actually test the functionality then also. There's a second loop. We can maybe check the robustness, and we even learn that there are gaps in the definition maybe in the ODD, so maybe we need to reduce it. So we have to rethink a little bit how we develop, and this loop we have to establish in an iterative way. Yeah, you have seen it on a more complex picture with the V diagram from Andreas. Second picture is the data needs. So also, I think well known, we have two disciplines. The one data need is on the training side. We need data for training, and we need data for testing. And I mean in this terms, to test the functionality, the outcome. And here a picture, if we have understood the ODD, for example, we can formulate, let's see, say this is a box, yeah, we can formulate the ODD border like it's shown here. Then we have to break down the task in what data do we have to collect in several tasks. This is not complete. You see the dots, maybe very small. But just as an example, there's some data we need to have for the semantic scene coverage. Okay, for example, we want to detect pedestrians. Then we have to see, we need some on the street, on the sidewalks, sitting, laying, standing, and so on, to have the semantic coverage. Then we need also the sensor effects, also what we have seen yesterday, like lightning situations, sensor challenges that we have to achieve. And then we have to get the seldom cases, the corner cases. Even they could overlap like we see here, and then it gets really strange to find that solution. For training, we need a statistical good representation. That should be the Gauss shape. And on the testing side, in principle, it's pretty much the same. You can see the breakdown is the same, but we need maybe another way of sampling. We need this statistical representation. We need to really the right dots, the right combinations of scenarios. And then a third question here on the industrial side is how can we produce, how can we get to this data? And I at least know the three ways. The first, the dark blue, is typically we start with recording vehicles, development vehicles, and yeah, we record everything that we can get. Then we already have a huge coverage but more the typical cases actually. But we can work with that, we can train the models. And then it's a good idea for the more seldom case when we come there to have access to a fleet, maybe even end customer fleet or whatever fleets. that you have drive that many kilometers, and that's what I mentioned before in that discussion. We have to have these triggers, these filters to find these rare cases. That's not so much, but it's harder to get them. And then even when we have corner case detected, then we learn maybe we need over that corner case, which is still seldom, a parameter variation. And that's a very good idea, I think, to use augmented and synthetic data. On the testing side, it's actually pretty much the same. Now let's switch to how we see it in the KI data tooling project. So we want to support the series development with different method sets. So we develop the methods. That's the work package that we have here. So 3 columns. The one is more on the synthetic data side. It's TP1 with creation and evaluation. TP2 does all the methods on the AI training, very important. For example, I rate the mixed training approach, how we can do that. And TP3 is all the methods that we have for creation, pre-processing, and running the real data. And each of these work packages needs requirements for the method development. So let's take one example. Here the AP13 who deals with synthetic sensor data. So what does that work package need? They need similar scenarios with similar content on real data and synthetic data. We call it that clone data then because we're cloning the real world. And that should contain sensoric challenges, like for the radar multipath reflection, for example, because only then we can see does the ray traces, does the sensor models work correctly and really reproduce these effects. So then this AP requests their data needs in form of a ticket, and it goes into our scene catalog, one example. And then that's true actually for, of course, all these work packages. So all our work package structure, we can separate in work packages that are producers of data, it's the blue ones, and those were users. And the users, of course, they request the data. And here have the list that we can see an overview, what the different users actually, what kind of data they need. So besides synthetic data, we have abstraction of sensors, and what they want to see is different modalities, of course, of the sensors, and also different positions, data of different positions, because they want to do this domain transfer work. The mixed training, they of course need different augmented real and synthetic data, and they need a lot of variations. It's very similar to the corner case, but also auto labeling, but with specific needs. Corner case, okay, the seldom cases like occlusion they want to see. Compression has another specialty. They deal a little with the formats, so they want real and synthetic data, but they need single and concatenated events. And finally, context generation, they also want to work with the infrastructure data because they're using the infrastructure data to derive the content. And finally now we have established a process. So what I said before, each work package can put a request they need just to find the purpose, what do they need, and specified the data need. Then we have a role as a gatekeeper. This is the working group Szenenkatalog. They check if the ticket and the request is the definition of readiness, if it's okay, do a prioritization, and then it's the question, is it a request for synthetic data? Then goes in the synthetic data production pipeline where a lot of partners, but also subcontractors work on. And we have the real data path. Yeah, it goes to AP 3.2. Here are the guys who plan the real data campaigns, and they have the recording vehicles actually, and then they go out and record all the data. So that was it actually from the requirement side. And now let's see, you have always the context, the people you can ask about these different topics. Then now I need to switch. Will you do it for me to the production part, or can I? It's already open, so escape and then the other one. Check. This is production. No, here it is. Yeah, then I proceed, but just for the first part, because first part in production is the synthetic data, and then Marcel will take over with the real data. Yeah, synthetic data. So I ended with the process how to set up the ticket. And now you can really see example of a ticket, ticket. So there was a data need for the guys who want to evaluate the synthetic data. And that's how a ticket looks like. So they want to have a scenario on a German Autobahn, and we identified the A9 could be very interesting. One reason was because there was already an open drive file available by another initiative. So we took that, and for the sensor guys, it was very interesting to have something with relative high speeds. They want to see like metallic reflections, again, for example, from the radar guys, for multipath reflections on the guardrails, and also a scenario like you can see here, driving below a bridge is very interesting from terms of sensor effect. So we took that, and that I want to have a digital clone of 20 kilometers, I think was on the A9. And we used also, in the middle, you can see the Pegasus model for more description of, for example, what objects you want to see there, how the weather conditions and so on should be. And once you have this ticket, then now the production process starts. It's a slide when you come in the afternoon session, you will see again. That's our workflow, actually, synthetic data workflow. So everything starts with the real data footage. So the sensor team analyzes and checks which scenarios are actually interesting, and they should then be reproduced, they should be digitalized. And then it goes, starts with once I have defined the scenario, then I look at in the asset catalog. If I have 1 minute, okay. If I have already these objects available in the catalog, then it's fine. If not, we let produce it. So we have a lot of partner subcontractors to produce that. Then we check a definition of readiness, create this dynamic scenario, and then it goes into the production line with the ray tracer, the renderer, and this is coupled with the sensor models. We check if the data is okay, and then it goes to the next ticket. And then finally here, just two pictures as a preview, because this in the afternoon you can see in much more detail here from Bitechnology. The outcome of ticket 48 on the Autobahn. Here's just some impressions from video where lens distortion, motion blur was implemented. Another ticket we put on addition on it that we want to have some dirt on the screen. And here on the right is an example for automatic generation of the trees and on the side of the road. And final slide, we are very proud actually, contrary to KI Absicherung, we have all three modalities. So we have a radar model already running. Here you can see first reflections simulated by the radar sensor. And of course, everything comes with a lot of ground truth, what you know and used to, you have see it on the list. And then finally, it's only to say for me, make some advertisement for the afternoon session. So if you're interested in these synthetic data, there will be a 1-hour deep dive, so that we can talk much more about it later on. And now I want to hand over to the real data path to Marcel.
Okay, thank you, Armin. I'm Marcel, the TV3 lead, and I will present the real data, the augmented data production, and the corner cases. Here you see our 3 recording cars. We have 2 fully equipped cars with LiDAR, video, radar, and reference systems, and 1 partly equipped car which has no radar, but the others are there. And additionally to this, we have the research crossings, 1 in Aschaffenburg, 1 in Braunschweig, where we record the infrastructure data, and here we have a lot of extensions, especially we have very good weather stations and also ultra high resolution cameras, wide angle stereo systems or high-speed cameras. What are the benefits of this recording constellation? So we can record the same scene from a lot of different angles. And additionally, we have the same scene from within the car. So we have the outside view and an inside view of all the scenes we want to record. What did we record so far, or which variation do we had? So we recorded different conditions regarding to weather or lighting. And we had a lot of special items. So for example, we had ladders, crutches, scooters, stroller, or packets. and we have scenes with low sun glare, or with rain reflections, or cloudy scenes. Besides the recording campaigns, we have the Freifahrten. The idea is that we record natural existing scenes or objects in the area of the recording partner. So, for example, trams or alleys, or half-timbered houses and cobblestones. During this Freifahrten recordings, we also did a recording in Renning on the proving ground, where we created the first digital twin in the project. So on the left side, you see the real recording, and on the right side, the digitalized twin. How many scenes do we have recorded so far? So we had 2 campaigns in Braunschweig, 1 campaign in Aschaffenburg, and the Freifahrten. So in total, we had 3,600 recorded scenes. Offline here means that they are recorded but not yet uploaded, and online means they are already available on the platform. Now let's come to the augmentation. Augmentation means we have a pre-recorded scene and insert objects or pedestrians or whatever we want there. Here you see the street and the pedestrian who should be inserted at this position. So we have to cut it out using a mask and insert it considering the lighting situation of the scene and other attributes. And another example would be to estimate a position or possible positions of a traffic sign. Here you see the 50 sign with different possible positions. And augmentation is also possible for LiDAR, or we work on augmentation for LiDAR. Currently, the state is that we try to reconstruct the scene first. So, because if we are not able to reconstruct it, we won't be able to augment it. So the first step is currently we convert the point cloud, 3D point cloud, to 2D images, height and the depth image, and use this with a gun network to reconstruct it. What you see on the right side, and the problem you see is, maybe I show it here. The problem is the images are really blurry. So this means if you convert it back to the 3D representation, the objects are completely smoothed out. So you don't see any edges. You don't see, for example, you have here some holes which are completely smoothed out. So we are still in an early state for the augmentation of LiDAR. Finally, the corner cases. Here is the basic idea. We have a scene which is semantically separated using a CNN. And we provide the semantical separation to the semantic driver here, and the real scene to the safety driver. And whenever there are different behavior between the two occurs, a corner case will be marked. This is the setup or the hardware, or the experimental setup. So you can, on the left side you see the semantic driver, on the right side the safety driver, and you can try this out by yourself in the room Brandenburger Tor, right beside the entrance. And how does a corner case look like, as an example? Wasn't your play? Ah, here, okay. Please, do you see my mouse pointer? No. You can look at this pedestrian here, which is visible on this side, but not on the semantic segmentation. So, and yeah, the neural network would overdrive him, unfortunately. Okay, if you want to know more for real data, there's Tobias and Clemens. For augmentation, it's Kevin, and for corner cases, it's Camille. Thank you.
Thank you very much, Armin, Marcel. As I already mentioned earlier, please don't forget to tweet back for questions. We're going to try and answer with everybody on stage in the final panel. Now we go to storage and enrichment, and I think I hand over to Thomas Beer. He's just let me sort this out here with the slides. Thomas is with Continental and giving us an overview now of what we are doing with data enrichment here. Is your PowerPoint? At least I was hoping to have it here. There you go. Stage is yours, Thomas.
Thank you. Thank you, Hans-Jörg. So, also a warm welcome from my side. My name is Thomas Beer. I'm from Continental, and I have the big honor to show you today the storage and enrichment parts of the KIDT workflow. So, yeah, actually, I'm pretty happy to see you all in persona after such a long pandemic break. So, yeah, hope you enjoy the day. Hope you enjoy my talk as well, even when it is pretty close to the lunch break. So, hope nobody is in the Suppenkoma. So, yeah, I do my best. Today I want to give you a brief overview about these three topics. We have compression, we have context data and the data catalog, and we have auto-labeling. Just a brief disclaimer. Due to the really tough time schedule, I can just touch most of the topics, give you a high-level overview. If we have some further questions, if you need some details, please feel free to contact the appropriate experts afterwards. I will show you the contact data at the end of my talk. Hopefully that's fine for everybody. So yeah, let's start with the compression of sensor data. So one of the objectives within KIDT is the development and the evaluation of so-called compression algorithms, so-called codecs, for various sensor modalities such as radar, LiDAR, and camera. Until now, the colleagues worked on C3 compression approaches. They worked on neural networks, triangle meshes, and an octree approach. I will show you the details just in a few moments. First, I would like to show you where codecs are applied within KIDT. So, yeah, certainly within the KIDT workflows, they are applied within the storage and the data management part. But even more important, when you think about making KIDT production ready, they will be applied directly inside the vehicle during operation. I think that's pretty important. So yeah, let me show the already achieved results. So the first one is about image compression using neural networks with one-hot max quantization. This codec performs significantly better compared to the known integer approach when dealing with low bit rates. And when I say performs better, I'm talking about the image quality. Just compare the solid and the dotted lines. So the next two are about LiDAR point cloud compression. The first one is a lossy compression of a sequence of LiDAR frames for long-term storage using a mesh-based compression iteratively. Being tested on data from Valeo, this approach allows a compression by a factor 25 to 30, thereby introducing not more deviation in points positional information. For sure, one may choose less fine-grained resolutions to achieve a compression factor up to 50, however, at the expense of higher losses in points precision. So the second one is the octree compression. It was developed using the point cloud C++ library. And the colleagues found out that the lower the resolution, and the resolution of both the point resolution and the color resolution, the better is the compression rate. And thereby, the calculation time stays constant, or at least does not increase dramatically. So, so far about compression. Let's talk about context. Well, everything in your life happens within a specific context. So we are all here, we are in Berlin, outside it's hot, and so on and so forth. Within KIDT, context is heavily related to a scenario. So a scenario, for example, could be a vehicle approaching a traffic light, pedestrians are crossing, and so on and so forth. And context data are describing such a scenario. Context data may include information about the vehicle, the road condition, the weather, and there are several more information stored or handled by context data. But from where do we get such context data? So we call it context data sources. There are several context data sources. For example, different sensors, camera, LiDAR, and so on. Also the CAN bus, for example, can be utilized. And here is an overview about the context sources, especially relevant within KIDT. So yeah, I already mentioned the CAN bus data. There's also, for example, a map database to get information about nearby objects. There could be stationary sensors for getting information about the traffic intensity, and also, and that's particularly relevant within KIDT, camera images. And I will elaborate on that in just a few moments. So why do we need context data at all? So within KIDT, we have identified two use cases. The first one is to provide an overview about the available scenarios, to do, for example, a coverage analysis or to identify gaps. And the second one is to enable to do an expressive and comfortable search for specific scenarios. And that part is covered by the data catalog, which will be explained in a few minutes. So here is a first example of a coverage analysis. What we see here, it's a time-based analysis, and we can see, hopefully you can see it, it's pretty small. We have data available for the first days of a week, but we do not have a lot of scenario data for the weekend days. The next one is about the position and the heading. We see that we only have a few with the heading between 0 and 45 degrees. So in addition to just use simple context information, you also can combine such context information, context data. For example, here you can combine the current location with the sun's position and the sun's elevation to infer potential glare situations for a vehicle driver, right? Okay, just a few words about the overall context generation process. Getting context data unfortunately is not as simple as just reading the data directly from a sensor. Now it's even more sophisticated. So, for example, you have to apply machine learning methods like image classification to get that data. Ich hab 20 Minuten. Sorry, I'm in time. Sorry. No worry. In general, the data, so context data is generated for both, for synthetic data and for real data, it doesn't matter. And from a technical perspective, they are stored in a structured way, they are stored in a JSON format. So here is an example illustrating the application of the image classification ResNet model. Applying that ResNet model, weather-related context data is inferred. So we see here on the left side, it's a rainy, cloudy day, and the following attributes are inferred. We have information about the sky, the precipitation, the road surface, the illumination, and the time of the day. And above the picture, you can see the values inferred for these attributes. So for example, you see for the left image, you can see the road condition, it's wet, we are during the day, and so forth and so on. And the right image, we see it's in the morning, it's sunny, and it's a little foggy, right? And all that information is inferred by applying that image classification model. So in addition to coverage analysis, context data are also a key enabler for efficiently finding specific scenarios. So within KIDT, we have identified two main actors. We have the ML expert and the safety expert. But both cannot just take all the data and work with the data. No, they have to explicitly use the data relevant for the appropriate use case. So, for example, when you're working with pedestrian detection stuff, you are especially interested in finding or having data including pedestrians, I guess. So, and that's pretty much related. I'm always a fan of finding some pictures to make some analogy to the yellow pages. So maybe for the younger people, yellow pages were not digital; they were a printed book, a big book. So I was born in the late 70s, so I don't know. I think there are a lot of younger people, so maybe you don't know that yellow pages. And that's exactly where the data catalog comes into play. A user, in this case ML specialist, is searching for specific scenarios, so it doesn't matter if these scenarios are provided by real data or by synthetic data. And we already have heard that context data is describing such scenarios or knows a lot of these scenarios. And that knowledge of the context data, again, is used by the data catalog to provide the results to the consumers, or in this case, to the ML specialist. Now as you have heard a lot about context data, let me briefly show you some technical details about the implementation of the MVP. In general, it's implemented, or it has been implemented using two different environments. We have the DXC platform and we have AWS Cloud. In the DXC platform, all the context data is generated and afterwards transferred and transformed into AWS. It's stored first in S3. Afterwards, it's transferred to a database. And from the user perspective, we're offering two things. We have a web application UI and also an API. So after so much theory, let me briefly show you how it looks like in practice. Come here. First, you have to authenticate or to authorize that you are allowed to use the catalog. Now, here we see the web application. You can specify several filters where you're interested in. For example, here we use the weather condition, and now you can search for or based on that filter, then you get an overview about the results satisfying that search criteria. We see we have real data here, only real data, as of type real data, also some data about synthetic data, and you can have a look to the related context data. Here again, it was an example for synthetic data, and this is an example for real data. We have always frame-related data and scene-related data. I did not expect that there are so many beamers, so I have to switch a lot. So, okay. So far about the yellow pages or the data catalog, and last but not least, let's talk about enrichment and auto-labeling. So within KIDT, labeling occurs in two different flavors. The first one is supporting the selection of specific samples being annotated. This is based on the assumption that there is a subset which is particularly relevant. And the second one is providing annotations directly. So this can be done, for example, by object detection, by tracking, and by cross-labeling. Well, that is done by these three approaches. In such an environment, the typical chicken-egg problem occurs. So we want to automatically annotate data, but we need labels to train our models, right? And therefore here, selection, annotation, and training is done in an iterative process, thereby incorporating the results of the previously annotated samples. So what kind of labels are generated? We have, to the upper right, we have 2D and 3D boxes. We have classes, we have semantic masks, we have meta-attributes and trajectories. So let's talk a little about data selection in detail. So data selection is realized using two different approaches, so active learning and criticality analysis. As I already have mentioned, active learning is utilized to identify particular relevant objects. And the diagram here shows that you can achieve a high object detection accuracy with low costs compared to random sampling. Or more drastically, if you want to have a higher accuracy, you have to annotate significantly more objects, right? So another approach is criticality analysis. For example, identifying critical situations. For example, critical situations such as the time to collision based on the trajectory data. Here we see a first example of direct annotations. So based on the image to the left, the tool, or better the model, proposes some labels, and the labels can be, if necessary, corrected by the human experts. The next one is about cross-labeling. Cross-labeling means that the information of different sensor modalities are combined. So, for example, if the camera cannot detect an object, maybe the combination of several sensors can do. And another approach is is tracking. So tracking fits very well for continuous data, and you can save a lot of effort as you do not have to annotate every object. For example, you only have to annotate only every, let's say, 10th frame. So here, to the left image, when t is equal 0, the bounding boxes are set manually. In the next step, they are tracked already automatically. The third image shows, if necessary, you could correct that object. And after several tracked frames, we already have a good velocity estimation. That means the tracking works already pretty well. Last but not least, until now we heard about approaches either the human was supported by the model or the other way around, the model was supporting the human. Here is a kind of combined approach where the results of, the idea here is to bring both approaches together by incorporating corrections. So for example, when a model does not recognize the arm of a pedestrian, a human can correct such a situation by correcting semantic masks, and this in turn is incorporated into the next model run or the next model prediction. So 20 minutes. Last but not least, here, as promised, the details of the appropriate contact persons we have for compression. Jonas, but Jonas can't be here because he's presenting the compression topic in a conference in the US. We have here Marcel, you already know Marcel, he's here. Yeah, you know me, Jan, is Jan here? I'm not sure. Here is Jan. Then we have Tobias is here, and Philip is here. All the guys are here. So thank you very much.
Thank you very much, Thomas. And we're handing over right to the training section presented by Thomas Stone.
I do have to change, right?
I can change, yeah. I'll do it for you.
Thank you. So, my name's Tom. Insert funny line here. Wait for reaction. Okay.
All gone.
I need a bad joke in the end. I needed it in the start, in the beginning. And what's coming now is probably not a joke. It's probably where everything that we're doing right now is coming together, right? So I'm doing two parts of the workflow. One being the AI training, doesn't sound too unimportant, right? And evaluation, also really important. Let's start. So I'm going to start with AI training. And in the beginning, when we talk about training, basically we have to talk about our pipeline, our workflow that we have in there, right? Because it seems like we have heard a lot about a lot of data sets, and it seems like this isn't the standard way to train any neural network. And it kind of isn't. So what we need to think about is, how do we train with different data sets? So how do we mix them? This is one thing I'm going to talk about. And also one thing that you need to think about is that if you have different data sets, they probably have different domains. And in our case, it's something for some parts we want, for some parts we can't change. So this is something we have to talk about and think about. And in the end, when we have trained our models, we want to be able also maybe to evaluate what we've done in some way, maybe even next to training. So this is also something we're going to talk about today. And maybe some information here about the downstream tasks. This is basically something like 2D or 3D bounding box detection, segmentation, so SEMSEG or instance segmentation. So these are actually the 4 tasks we're trying to work on. So first of all, domain adaptation. This is a really nice thing. It's basically if you have a real data set and a synthetic data set, so that's what we call them, then what you actually want is to get the last bit of your synthetic data set. So basically the last mile to get your the synthetic data set to look like the real data set. Or to make it easy, if you look at the images down there, you can see on the left side, that's what rendering looks like with color right now. On the right side, that's reality. Everyone can see there's a difference, right? And it's probably going to take us some time to have rendering pipelines who can do this perfect and perfectly realistic, and also the artists have to come up with ways, produce data, so we can render it very realistically. But in the end, we're always going to have this little bit of delta that we're missing so that it looks like on the right side. So what we need is to basically change every sample that we have out of the synthetic data set and make it look like on the right side, which means it's something that we call domain adaptation. We want to take something from one domain and take a sample out of it and make it look like it's out of the other domain. And here we have a few nice examples that we have created, where you can see that we take on the left side, on the lower left side, you can see that we take synthetically, so rendered images. We take a little bit of labeled data, so our segmentation, and with that information we can produce something that looks quite right or quite realistic. It's not perfect. You can see that some things don't look quite right on the street, especially with the guiding lines and so on, but it looks quite nice. And I hope that you will think about going to this deep dive. We have two special GANs. So GANs basically are the method that we choose to do our stylization or our domain transfer. And I think they can tell it much better than I can tell you here, and they have much more time. So if you're interested in how this works to make something that isn't really realistic, really look like it's real, then go to the deep dive. So the next thing is, now we have talked a little bit about domains, and you can see the deep dive later on. What's also important is, of course, like I said before, we have something of we need to mix data, right? So now when we're training a neural network, we basically do this in epochs. We take a piece of data, one data set, we throw it into the network, and we get out a new network, right? The problem here is we have now 2, 3, maybe even 4 different data sets. We don't know. There could be many data sets that we want to mix in the end. So not just one synthetic data set or one real data set. And there are 2 kind of big strategies right now that you can use. One is for mixing data. One being you either use this epoch-wise training, and after each training set, you look at your data set, maybe how it worked, or just some static way, and change the kind of the domain through just randomly taking new samples in from maybe some new data set that you have, or just throwing out samples out of it, and then you take this piece of data, it's your new data set for the next epoch. But you can also do something that's called batch-wise training, batch-wise mixing, where you basically, for each batch that you throw at the network to train it, so something like a set of images in our case that the network looks at and trains upon, that you have some kind of mixing strategy in there. So there are many different possibilities there, and this is probably one that we're going after in the next few months. Also, maybe interesting to see something. We had a comparison about data sets, synthetic and real data sets, and what's really nice to see here, the comparison between, on the left side, the kiddie data set, so this looks quite real, right? And on the right side, you can see it looks quite real from the far, but this is from virtual kiddie. It's not real, it's a synthetic data set. And the comparison is very interesting because there are many things that are different in both data sets. Like sometimes on the right side, you have a lot more ground truth and so on. So this was kind of important to see when we're going later on to use GAN methods to change the right side to look like the left side. I'm coming to this point later on again. Now, another piece that's really important is, well, if we, like in the beginning I said, we want to change the way we are training, we want to maybe touch the training itself while we're doing it. We want to evaluate what is happening while training, maybe in the aftermath or before. We want to see what can we do with the data sets that we have. And one thing that when we look at data sets is that what we're sometimes missing is, of course, corner cases. And now this image is quite nice, but because it brings together a lot of different corner cases that we have. Like, there's a lot of snow. This is maybe some kind of corner case. So from experience, I can tell you, driving around in winter isn't something that always happens nicely when you have a test car. On the other side, you have like a skier here in the middle in the image. Then you have a saturated portion of the image in the middle where there is sunlight. Most of us could drive there. Maybe if you have a neural network that sees this, maybe it just shuts off completely. You don't know. So there's a plethora of corner cases that you may be interested in while training. So we need also a structure, so a structuring mechanism there. And one way to structure a corner case is to structure it in one part sensor layer, content and temporal layer, and also methodical layer. So for the sensor layer, this would be something like we've seen before, where you have a saturation of pixels. So that's also physical level. And on the content layer, you may have something like you see a person that's on a billboard, and your neural network may be really good at detecting persons, like with your camera. When you look at a billboard person, they will see the face. At least with my Samsung phone, it does that. But when you're driving a car, you may not want this. Also, the temporal layer, also very interesting things that are happening. If you have like a person that breaks a traffic rule. And then last but not least, of course, the method layer again, where you may be interested in some things like adversarial examples that we heard something yesterday about, or just the uncertainty of the model, how it influences how your detections work. So one way to see corner cases, to detect corner cases, is if you use your model and you try to figure out how uncertain it is about some detection or some segmentation or something. So if we go at 2D detections, you will see what you can do is you can take a standard model, a simple one like the mask or CNN, and you can do some Monte Carlo dropout, and you will get for one object that is detected several different bounding boxes. And what you can do is you can plot it and see how those differ in values, like where they are or in size, or what class they have. So in the upper graphs on the left side, you see that it's kind of uncertain about, is it really a bicycle if you look at the bicycle next to the car? Or sometimes it may think it's a traffic sign or cat or something. So it's quite uncertain about this bicycle, and this is maybe some indicator where we can choose, okay, this image has to be in our corner case data set. What's also very interesting is when we look at what our models do, sometimes they're really bad at things that we are, as humans, really good at, like when something is obstructed in some way, occluded, like there is half of the person missing, maybe even mostly everything except the head. We see the head and we know there's a person behind, if there's a car in front or something. So our networks probably are missing something there. And maybe the hope is that we can do something that's called amodal segmentation, or amodal perception, in this case, where you say there's, we hallucinate, or we want our models to hallucinate something that it can't really see completely, and therefore it may get better at detecting that it's there. So on the upper left side, you can see, on this image, there is a bike. I hope you can see it. There's a person in front, then there's also this thingy in front here. So you can only see parts of the bike, like actually just a part of the tires on both sides. What you would normally have in segmentation, probably your network is bad at detecting that it's an overall a bike and would just maybe find one tire or something, which is in the middle image. And on the right side, if you do this with amodal segmentation, you can find that your model may get a lot better when it knows that when it tries to hallucinate objects that are occluded in one way or another. In the lower image, you can see how this actually looks like. So in the middle, you have the segmented image like you would have normally have it. And on the right side, you can see that while this person occludes the truck behind it, you can see now that the model checks that, oh, there's a truck behind that person because I see 90% of truck, right? And the only problem that you have to change a little bit about the labeling. Because usually we only have this kind of label where we have the foreground labeled. And now you need everything in the back also to make it good. Next thing also, we have corner cases in trajectory where we can say it's interesting sometimes to look at how we move, how our traffic is moving, how the environment is moving in some way or another. So maybe it's interesting to see just that someone is doing something illegal, which we usually don't have in our data sets. Like something like a left turn when there's no left turn allowed. So Maybe we want data of left turns, of people doing left turns, but they shouldn't be doing left turns. So this should be something that we should have in our data set. I live in Munich. I have one crossing where this is happening all the time. So this is something we need in our data set, right? This is a corner case. Now, we talked about corner cases. We talked a lot about domains. We talked about mixing stuff. But there's something still missing, because one usual problem that we have is someone comes along and tells you, you know, I got a nice testing car, and it's got a completely different setup than we usually have. I want to see how good your method is on that. And you can't say, yeah, then go out, drive 1 million miles, give me the labeled data, in 2 years we're going to meet up and I'm going to do your stuff. It takes about a week of training and everything is fine. That's not going to work, right? So what you want to have is some kind of sensor data abstraction. And what we did, we said we wanted 3 different things that your data abstraction, your sensor abstraction should have. Invertibility, robustness, and interpretability. It should be, whatever you do, it should be robustly working with, so your network should robustly work with the abstracted sensory data. That is something that is obvious. Also very important, at least to me, interpretability, because what you also want is, if you're an engineer and you want to see where your networks fail, you do a lot of working with the sensor input, right? So if you have a lot of sensor abstracted data lying around and you do some engineering, you want to be able to see easily what the sensor data is representing. It's also not really easy. So here a small video. I don't know how much time we have for that. I forgot to. So what you can see here, we have some detection algorithms running in a sphere projected LiDAR point cloud. We have all these detections in the upper side, and then you can project them back into this not so abstracted version, so the point cloud itself, and you can see still easily what is happening when you back project everything. So depending on the abstraction of the sensor you work with, maybe it's just still easy to see what is happening. Actually, both parts here. So the last piece, evaluation. So for evaluation, we talked about different domains. We talked about real data. We talked about synthetic data. What we actually also want to know is how far are we away? How big is the gap from synthetic to real? Maybe we want a rule or something for that, or we want just something that says this is not good enough in some way or another. But it's not quite easy. What we do, we are currently working with images and trying to categorize our metrics that we develop there and that we test there in realism and quality. So one part is, if you look at the images that you get out of the rendering process, they don't look real. We see that pretty instantly. Now we want to have a metric that does the same, and it's not quite as easy. If we go further, you can see we have a very simple metric, like mean squared error, some signal to noise ratio variations, but we also have used things like variational autoencoders just to have something that tells us, is something real or how real is something? And what we can see on the right side, it's not easy to have one metric that gives you an indicator of how realistic something is or how realistic something is not. So in general, it is like we need a baseline, and this is what we're currently working on. But it's not easy because every metric we have works on one part of a data set, but not on the other. So we have something that tells you here, this is not really realistic because of the toning. And on the other side, we have things where this would say this is totally realistic, but on other samples, it would say this isn't realistic. And to the end, then there is also the quality part. So we had this, what we call realism, and now we go to quality, where we say, now we should look at how good is our data set working for the task, for the downstream task that we were working on. And it's quite interesting because there are many things that you wouldn't think about beforehand, right? So what I want is, I want to check, is our synthetic data set good for the training and for evaluating and for getting a nice function that works and having it work safely. And then you will see when you work with a real and a synthetic data set and do comparisons there, that sometimes you have very simple problems. Like one problem would be that the amount of ground truth data is different on very simple clones of each other. So on the right side, you can see a comparison of kitty and virtual kitty from the corresponding samples. And then the lower image, you can see that you got all the 2D bounding boxes as ground truth printed into the image. On the upper side, the same with the real data that we have. Now, if you look at it, you will quite easily see we have a lot more boxes down there than up here. So depending on how you, depending on how you compare basically how your network works on the real and on the synthetic data set, you will have a very different way of saying this is a good fit or a bad fit. So we need also here some kind of balanced way to basically maybe prune some of the ground truth that we already have in one data set, or a different way of measuring how good we are in the overall compared in both data sets. So, good. That was flying through. So, because I didn't do this myself, there are a lot of people I want to thank for this piece of work, and especially Max and Claudia are going to have a deep dive that I hope you will consider visiting. And thank you.
Thank you very much, Tom. So as Tom already mentioned, we're going to have a number of deep dive opportunities now to look into some of the topics at more length, with a bit more insight into also what has been achieved so far and what the current work items are. We're going to go split up in several rooms, but first of all, some of the pitch work needs to be done to entice you into specific sessions. So you need to decide now which sessions to attend. We're going to have several in parallel. And I probably let Claudia quickly introduce her deep dive session first, which is about the style transfer domain adaptation with pretty impressive latest results.
Yeah, so hi, I'm Claudia. Maximilian and I will tell you something about domain adaptation from synthetic to real-world data, and our aim is to enrich and enhance the synthetic data to make them look more photorealistic as possible. And we do this with GANs, and GANs are a very, very cool topic, and the results are also quite impressive, so we hope you will join us.
Great, thank you. That was deep dive session number 1, and then we have deep dive session number 2, which will look much more deeper into data production. And Armin, you're gonna go give.
Does it work? Right, okay. Do we get the picture, or
we don't get it?
Don't get a picture. It's animated, but yeah, whatever. Okay, deep dive 2 is about synthetic data production and also evaluation. So we have a full hour deep dive, 5 presenters, and we take a journey with you through the production cycle, but also first evaluation results. You can see, I mean, you have shown this picture already, but let me introduce the speaker, so what you will hear. So it's from dSpace. Thorsten Püschel will tell something about automatic scene generation out of real data. Then from Machivision, you will have Markus Bartnick, where show dynamic asset production. Then we have bit technology. Karl Leis will present about the rendering engine, physics-based rendering, coupled to the sensor models. And finally, André Skusa from dSpace, once again, he will make the back loop and show the first evaluation results of the video data, which metrics actually we rate, and how we evaluate them.
Excellent. Thank you very much, Armin. And just to go quickly back to the first pitch about style adaptation, Claudia, that would have been your slide, but I think you made it pretty clear already, right? And then there's a third deep dive, fourth deep dive actually, besides the presentations. There's also still the poster session which will open, and we'll have a deep dive number 3 on data annotation and data automation. And I think that's yours, right?
Hi, so I'm Jan. So when we want to train our models, we need a lot of data, as we all know, and but just the data is not enough. We need some actual annotations for this data, be it boxes, segmentation masks, or class labels. And in this deep dive, well, we'll dive deeper into how we actually annotate this data, how we select which data to annotate, and our partners from Understand AI will go into more detail about how they process the project data and actually automate this annotation process and make it less costly.
I already heard several times over the gross domestic product of Germany involved in labeling costs until final production of a level 3 or level 4 product. So this is going to bring that cost down. Let's see how much of the gross national product you will be able to save, right? Anyway, we're going to have those sessions separate in rooms. So we have room number 1, which is the main stage here for Deep Dive 2. We'll have room C2. You see that here on the slides, which is on the opposite side of the building here, room C2, where we'll have Deep Dive 3 and 1. And on the other hand, poster session is still open in room P, where it used to be during the lunch break. So you have an opportunity now to go for a full hour into those deep dive sessions, enjoy and discuss, and bring back many questions, because afterwards we're going to, of course, collect also what you put into TweetBack and hopefully answer those questions in a final panel. So enjoy the afternoon. Thank you very much again to the presenters.
Hallo, hallo? Das geht? Das noch?
Okay.
Okay, we start. Last people are coming. So welcome to the afternoon session. Very happy that now it gets into more technical deep dives. I think it's going to be a really interesting part what we show here. So 1 full hour about synthetic data. So session is called Synthetic Data at AI Data Tooling, Goals, Challenges and Solutions. And yeah, I'm very proud to have can announce a really cool team. I think we're 5 speakers here. That first leads really to the production cycle, like I've told, of synthetic data. I have only a quick part about trends and challenges, and then Thorsten Püschel from dSpace will show us about scenario generation, really produced out of the real measurement data from the vehicle. Then Markus Bartnick from Mackevision, the making of, movie maker of dynamic assets, motion capturing will be explained, real cool. And Carl Leis from Big Technology will show then the rendering engine and for physical-based rendering and the automation. So that closes the loop. And even we have a bonus material, so to say, from André Gusa from dSpace once again. So the first evaluation results. I mean, there we will show definitely much, much more at the end than the final event. But here already you can get a first glance about how we would evaluate what metrics and so we are using. So really good team. I'm really interested and proud to show that. So let me start with some trends and challenges for the motivation. The trends, for the trends I want to take a look overseas to the Silicon Valley. So we have the well-known guys which are heading away in this discipline, Waymo and Tesla, well known. And I think these 2 companies, certainly are those who could say they have a huge amount and access to real data. So, but still, they are investing a lot in synthetic data, and that should be for us indication that we also should care about that. Otherwise, they would not do it if it's not necessary, not needful. For both announced that actually last year, pretty much. Waymo, they had a simulator running 2000, or they announced it 2017. CarCraft, that was more for behavior simulation, but then they told last year that's not enough. We need physical-based rendering for perception development, and then they came up with a Simulation City. It's another simulator that decided to have 2 different things. And Tesla, also last year on the AI Day, they showed about their simulation tooling, and here impressive numbers of how many millions of kilometers they designed. On the challenges side, we have identified 3 important challenges. This is what even we have synchronized and discussed it with KI-Absicherung. It's first the data quality, of course. I mean, very interesting or very important for validation. So the trainers say if it works, it works, okay? But for validation, we have to have trust. So are the data good enough, not perfect, but good enough to train models and that we can trust it. Second part is the automation. So we need to find a way to translate directly requirements automatically into scenarios, build the scenarios and the data, create digital clones, and do variations. We have seen that complex amount of variations that we want to produce that needs to be automated. And the last point, cost and effort. I mean, automation also would help for reduced cost. But another thing what we've identified is reuse and exchange. So once we have one byte maps or generated and bought maps, mesh, assets, materials, we should make it should be possible to reuse in other tool chains. We don't want to invent or buy it a second time when we change the tool chain. Very important. So that's standardization is important. And then I want to just introduce our goals. That's our target pictures of the TP1, where we all do that. And the goals, and the big goal is really establish a method set
to validate the synthetic data pipeline. Of course, we have this synthetic, that's the sign here. We have a synthetic data toolchain and pipeline, but that's not the major outcome. That's coming from the partners and the subcontractors. What we are doing here, that's one I've already mentioned. One outcome would be that we have this synchronized interfaces for reuse. That's one thing, and the other important thing is the method set to validate this toolchain. Is it good enough? And everything starts with a scenario catalog. So we collected a lot of scenarios for each modality. The sensor experts said, this scenario I need to evaluate if the production was correct, okay. So I've already mentioned it for radar. I like radar very much. It's multipath reflection or microdoppler. You need to see these effects then in the synthetic data and compare it to the real data. Then we produce, of course, the data, and that gets stored also in our data catalog. And what we're looking for is this clone data or data pairs, we call it often, the similar pictures or frames between real and synthetic data. And then there comes the metrics. Very important. We have set up a big catalog of metrics, how we can evaluate it. We also have to check about the formats. You can only rate the metrics if you have defined the right interface and formats. And these metrics we need to bring into evaluation scripts. And we have a huge amount, and now the big questions we are not through. We have not answered completely, but first indications, André will show it. Which are the right metrics that we can use for evaluation? And these right ones we want to bring in a dashboard, and André will explain much better later on, but a first idea, what I think very important is these three layers actually where we want to put the metrics on. So the first is on the sensor parameter layer. So for example, do we have modeled the field of view correctly? It's the first. Second layer is more where we look into the physics, into the effects. We do correlations. We look at similarities. That's on the physical level. And the third is on the final level, really in the function itself, on the perception. Could be either at a final result, the perception AI outcome, MIOU, precision recall, whatever, but also in between in the latent space to look at features. So the metrics are all, or should cover all these areas. So that's it basically. That one I would skip, I have shown before. So we go through that journey, and I want to hand over now to dSpace, Thorsten Püschel, with the first part.
Thanks, Armin.
But you need that.
Thank you. So good afternoon also from me. My name is Thorsten Püschel. I'm product manager at dSpace in the area of simulation models and scenarios. And yeah, today I want to explain you on the topic one topic where dSpace is contributing to the project KI data tooling. And we contribute with a tooling, as the project name says, to generate simulation scenarios based on real-world measurement data. And why are we at dSpace working on this topic? So this is because we think that real-world scenarios help to solve the challenges that we have in the topic of validation of ADAS and AD. And I want to start with introducing some of these challenges. So first of all, if we talk about validation of ADAS and AD systems, you need the right scenarios. You need a scenario database with scenarios that really fit to your ODD, so to your operational design domain. And by using data that you recorded in your test drives, you are sure that these scenarios fit exactly to the operational design domain you intended your system to work in. The second topic is, of course, the test coverage as a whole, so especially the corner cases. We heard about this before today, that corner cases are quite valuable to know. And if you experience a corner case in a real-world test drive, you don't want to lose this information. You want to be able to reuse this in simulation over and over again to do also your regression tests in later states based on this. Then we have the topic of realism and complexity. So, of course, the real world is complex, and you want to have the same complexity in the simulation. Finally, also this morning in the panel discussion, Armin mentions this. the reduction of unknown risks. So by continuously setting up a process that monitors your system in operation and monitors risks that you experience and brings this into your scenario database, by this you can decrease your unknown risks continuously while operation of the fleet. And finally, also one topic which is quite important for us is the validation of the sensor models. So by being able to compare real-world measurement data with synthetic measurement data, you are able to somehow judge how good your sensor models are. And this is especially the topic we are working on in KI data tooling. So this is the whole research question, let's say, in this work package 1. So before I go into detail about our scenario generation service, I just want to introduce what we at dSpace understand under the topic scenario. So this is a term which is used quite widely. And we use a scenario for simulation, also for setting up closed-loop simulations, for especially validation of ADAS and AD systems. And we see basically 2 parts in there. So that's the dynamic content and the static content. And in the dynamic content, we see the maneuver, which is the definition of how my vehicle under test has been moved in the scene, and the traffic, which is all the environmental traffic, so other vehicles, other pedestrians. And this is typically described as open scenario, so that's a standardized format to describe scenarios. And also with this kind of scenario definition, you are able to change parameters of the scenario and change the behavior. On the other hand, we have the static content, which we again separate into a definition of the road network, which is typically described as an open drive file. And especially important for sensor simulation is, of course, a 3D scenery. So you need an accurate representation of your environment in 3D to be able to do accurate physics-based sensor simulation. And with our tooling, our scenario generation service, we generate all of these four data artifacts that are required for the simulator to work by our scenario generation service. So here is shown how it works in principle. So we have basically 2 steps. So the first one is a scenario extraction, where we analyze the raw data and extract all the relevant information from the raw data. So for example, detecting the positions and trajectories of vehicles in the LiDAR point clouds and on the camera data. And this data is then stored in a generic scenario description file, which we use then in the second step to produce the simulation scenario for the target simulator. In this first step, the scenario extraction, we use the annotation and labeling tooling from our daughter company, Understand AI. So there are again 3 parts: road extraction, so extraction of all the lane information and the parts of the road, extraction of static objects and dynamic objects. And this information is then used in a second step to really create all these data artifacts that are required for simulation. So, this first step, the extraction from the raw data, as I said, it uses the labeling tooling from Understand AI. And depending on the use case of our customers, we can either have a fully automated extraction there, which may be not that accurate, but for certain use cases this might be sufficient. But we can also apply manual corrections on the labeling, quality assurance that Understand AI offers to have a quasi-ground truth information extracted from the raw data. So here you see the result of the scenario extraction. So this is the abstracted representation of the simulation scenario. So you see the road information with the labels and also the road markings, the trajectories of the detected objects, and also the positions of all the static objects in the scene. With this information, we run a fully automated process to create the data artifacts for simulation, so the description of the road network in OpenDrive, and also a scenario description, so a definition how all the dynamic objects move in the scene. The third topic is, of course, the generation of the 3D environment. And for this, we follow two approaches. So one is, quite simple, let's say, or quite obvious. So based on the labels based on the raw data labels, we just place available 3D assets in the scene. So, for example, if a traffic sign was detected, it's quite obvious to put a traffic sign from the 3D library in the scene. And so we can already fill the scene with available assets there. And the second method we use to complete the scene is procedural generation. So here we follow a tool-based approach that we can integrate the measurement data into our tooling and parameterize our procedural generators according to the measurement data. So for example, we can define the building outline here, and our procedural generator then creates a building with random properties. We can also add further properties to the or further parameters to our procedural generator, for example, adding the facade color, and then you already have the correct color here, or even add the window layout. And with this approach, we are able to scale or control the effort that needs to be put into the reconstruction. And here you see a video of my colleague working with the tooling. So he's defining the building outline here, and also the height of the building. And our generator then creates here on the right side the geometry according to the settings he made there. So now he is defining the window layout. He is changing the facade properties, the colors, and adding more and more information into the procedural generation process to finally create the geometries here. And it's worth to mention that the procedural generators, of course, create 3D models that are suitable for physics-based sensor simulation. So all the material properties, so for example, the window frames are containing suitable material properties, for example, for radar simulation, because it's metal and it's different than the facade. So, I think the video is done now. So you see it, was quite fast to create this building here. And finally, as a conclusion of my talk, I want to show you first results. So here we have used object detection network. So it was a simple YOLO network to detect vehicles, and put this or let this run on real data, which you can see on the left side here, and the synthetic data that you can see on the right side. And as you can see, the object detection algorithm works on both data quite similar. And within KI data tooling, we hope that we can somehow use the methods that are developed to judge or to calculate KPIs, how good this correlation between simulated or virtual data and real-world data really is. So this is now data that we used from our previous activities. We also plan to use the data generated or measured in KI data tooling, of course, in the future. So with that, I pass over to Markus. Thank you very much for your attention. And Markus.
Thank you.
Here you go.
All right. I'm Marcus Bartnick from Mackevision, and we have the honor to participate in this project. We have taken a small part, it's called GUA 5. Mainly, we have 3 categories of assets, dynamic assets we are producing. Those are characters, cars, and props, so like bicycles and stuff like this. And I will show you in the beginning how we proceeded with a different type of assets. So we started with characters. Those characters have a rig with bones, and a skinning on top of it. We are starting in a T-pose topology, and those characters are exchangeable. So all the animations we are building up are exchangeable between different characters. The main feature is that male should be male and female should be female, and the height difference is about 30%, but other than that, the characters are exchangeable. After we generated those rigs, we started with a motion capturing. You can see over there the setup. We had some cameras, we had a motion capture suit, and we did markerless tracking on it, and we had a female. Sorry. Some technical issues, I'm sorry. So can you hear me better now? Perfect. So we recorded a male and a female actor, and they did all kind of poses and interactions with it. We have done this in KI-Absicherung in GUA 6, and we have done this also in data tooling, and it's pretty much the same process. But we did this time the process with props. So we had a bicycle, we had inline skates, we had all the different kind of things. And yeah, you will see a 360 later on of all the assets that we did produce. Yeah, I will just proceed with it. Here for KI data tooling, there was a special issue that we have radar in the properties also. So we had a special material, or we have a special material on all the metal parts being reflected in radar detection. And for example, here with the e-scooter, those are metal parts which are colored, and there are some rubber parts and some plastic parts on it. Now we'll quickly walk you through the different characters we did produce. So different walk cycle, every character has his or her own animation, and those animations can be exchanged also. All the characters have some creative names, so the person who did create it had the possibility to give the naming, so that's why they have some funny names in there. Here we have some interaction with the traffic. The police guy here has also some metal parts, so the gun and the, I don't know, those keychains? Handcuffs, yeah, that's a word I was looking for. The handcuffs are metal parts, and you can see it in the radar detection also. Of course, we need a female police officer also, and we are working right now on a BMW police car. This will be in Sprint 2, where you can also, so the 2 police officers can use it there too. Okay, some more walk cycle here. Female and businesswoman. And bicyclist. So we have a nice motorbike here, some retro motorbike. And all those assets are generic, so we have no legal issues. This was a big issue for KI data tooling also. So everyone, we have the possibility to exchange it between the different vendors. So here you can see some of the props. Oops, sorry, this was too fast. Some are missing. I don't know. You can see at least some of them. E-scooter is there, motorbike is missing, and the inline skates are missing. And now you can see some of the cars. Some of my movies are not working here. That happens if you don't test it beforehand. I'm very sorry for that.
Which slide is it? Which number?
34 and doesn't work anymore.
We look on our machine. It's here. Just a second.
Okay, now something is happening, but
We have a problem too. No, this is yours.
the presentation I did upload was working. I'm sorry for that.
It's on my machine, right?
Yeah. Here we go. Yeah, I will just say next slide. So could you please start the presentation? So you can see that all the cars have a 360 with different lighting situations, different lacquers, and all the materials are being separated, so for also radar detection and so on. Can you go to the next slide? Yeah, just run through it. And finally, we have also a different car brand. So we have the first time a Mini in here. So we have some cool assets for other target groups. So this should be the last one, and then there should be a movie afterwards. Okay, perfect. So we did talk about the domain gap before. And I wanted to give you a quick sneak peek what we have done with procedural environments so that we come very close to a very photorealistic environment. First, we did start this setup as a proof of concept for marketing purposes for a German southern OEM. And now we have done it and implemented it already on the homepage also. We have done a huge street lane with about 12 kilometers and have done different setup points. And what you can see now is that the vegetation is being exchangeable and being adaptable. So you can change a tree with a bonsai tree. You can change the weather conditions and everything. And we have the possibility to do it also in Unreal. And start with the show. There should be music in there too, hopefully. No music for you? Okay. Yeah, I don't know if this would be feasible. Here we go, perfect. So all the water and everything you see here is synthetic. There is no real footage on here. All right, that was my little presentation. Thank you very much for the time I had here. So Carl, you're in the next one.
Hello everybody, my name is Carl Eis. I'm CEO at Bit Technology Solutions, and I give you an overview about the physical-based pipeline we use in data tooling to generate synthetic data. First of all, I want to also thanks everybody for this great event here, the first day with KI-Absicherung. And I think in data tooling, we can now leverage all the work which has been done so far and continue building on that stream. Yeah, this is the next one.
Yeah, just a second. You can go one back, please.
Also hier schaltet er um. Your video was too big. Vielleicht nochmal zumachen, aufmachen. Und jetzt auf F4, auf Link, dass wir direkt reingehen. Okay, good. Then let's continue. What are the main steps? Well, we decided to make an open, modular, scalable platform which helps you to generate the data you need at the end for your use case. Since this is a big task, we have partners on board, and I'm pretty glad that we made this setup together with Bosch, with Intel, and with Valeo to establish a complete new way of working together to generate such data. Before I go in the next slides into those modules, into those generation steps, what are the main three process steps to come to such data? Well, we saw the assets, the scenario extraction process before, and everything depends on the input models. Assets, so 3D models, geometry, plus the materials, but even more important, the behaviors which AI recognizes, which give us the relationships in the traffic. Map data also important. Here, OpenDrive, other data is utilized to procedurally generate 3D worlds without having any artist being sitting on there. As a reference, scan data, laser scans are utilized to either reconstruct or to make a reference to the generated worlds. Last but not least, the sensors play a very important role in such physical-based rendering process. How could we generate data which should look real without having the sensor artifacts included? The next step are the scene generation steps. Here, it's a more complex process, which is not just one monolithic process, but a set of different modules which help to generate those artifacts in a procedural automated way, even with the help of AI, where it scales and where it brings the efficiency up. Data analysis is important to understand where is which quality in the assets. Features are extracted, and physical drive simulation of car damping system, mass,
engine brake behavior steering angle is applied to the first static generated worlds and then enriched with dynamic cars and pedestrians. Those animations then can be varied in a completely automated way to give you billions of scenarios. And even more, virtual characters, as we just saw before, are put to the scene to make it look even more real. Even scene generated by AI is a big topic to place assets which are kind of learned from real dataset streams. The last process step is the actual sensor processing, which is one of our biggest portions in data tooling, where the high definition ray tracing happens together with Intel, the Osprey toolchain, but also with alternative modules from our end, which we use, for example, in KI-Absicherung. The speciality we bring in this project is electromagnetic ray tracing. This is something pretty brand new. Why? Because it combines effects of normal ray tracing with electromagnetic wave simulation. Also, neural rendering is a topic which makes this topic even more interesting and scalable, you will see later on, as well as orchestration for cluster. And this not just for the automotive industry, but in many other projects where our technology is already used. Aircraft and also the train industry. Now let's come to the models. What is a good model actually? Well, input data is key as we saw. What are the challenges? Accuracy of the models. So geometrical specs, having no voids in the system. We do want to not have black areas or sky inside of the model, so it's pretty important that these models are complete. That the thing is kind of complete from a topology also, Harmonized specifications, meaning the naming conventions, the way they are structured, the skeletons of the people. Widely and open formats are important. This is also one of the key aspects in data tooling. GLTF is a key format to allow us the interoperability between the different partners and tool vendors, not just in this project, to make all the assets we have usable in this consortia. Then the physical parameters come into the game, how to deal with them. And here we developed an extension together with other partners, which is called Open Material. We published it and we generated the first scenes with that. What is the benefit of such physical parameter set? Well, you take a physically measured value with the physical quantity and you use that for physical calculations instead of normalized values, multiplication factors, to have that later on as a real ground truth also available. That's a big step towards the proof of how transferable are synthetic data to real data. And of course, for variation and consistency at the end, the amount of asset matters. I mean, today, and that's probably the biggest limitation, as we also heard in other talks, we are generating scenes with procedural effects and other measures, GANs and so on a few assets. But if you look on a real scene, we talk about 5,000 assets if you just drive a few hundred meters. And that's actually the push I want to give here, that we all together in a sharing community should invest into making this large asset pool, because everybody will profit from it and make the scenes even look better. And with those assets, like putting stickers on it, doing variations, having those pedestrian models, there's even some coming from our end, we can then do all these known principles to multiply them and make the scenes more usable for our AI training and testing. And this is kind of the pipeline we do, that this pipeline serves not just for training, but also for testing purpose, and that in a manner where the feedback of the test can be directly utilized to feed it back to the beginning of the pipeline. Here we see, for example, what has been done in KI-Absicherung, which is something we are putting now more effort also in data tooling. Taking open drive, open scenario, public and own data sources, such as our asset catalog, to really automatically generate those scenario variations. You see all the small black spots, which are pedestrians or cars, which gives you billions of variations. The idea is not so much to do it maybe systematically, but to set boundary conditions and let the engine generate data with all the meta labels, which allow you later on to filter it. And you get always, and we have those proofs already, you get a lot of situations and corner cases even without thinking about it. And as said, real data scans help to either speed up that process or to use it for a reference check as a quality gate. Animations I talked also about, but what are the animations and how to make them scalable? Well, light situations is something which can be controlled in a very nice way in the meantime with physical-based procedural sun models. But also the traffic animation itself, we built a framework which makes its own path planning based on learned real data so that it completely looks realistic. Exchanging with AI methods the surface road material so that you don't have to put an artist there to generate those materials, map it there. This can all be done automized. And of course, where you're driving, the way, the scene, inner city, highway, freeway, doesn't matter. Sensor positions, arbitrary meta worlds based on little input data, multiply it and process it. With that, that's our vision. We can make our contribution to the domain complexity and the usage, not just of this data for AI, but with the help of the AI. Ground truth and metadata is the next topic, which is important. I mean, we have seen in the last days the different labels. Apart from the classical ones, I just want to focus here really on what is actually new. And that is kind of the complex behavioral descriptions which are put into JSON formats. And not just that, but also the way you can track objects over kilometers. Here we, for example, have a A9 highway scene, which was started to be generated for data tooling. It's a 22-kilometer long setup where it's completely procedurally generated, and you have all the labels there. Doing that on real data might be a kind of big effort. And every pixel, every ID is kind of unique, can be tracked back to the catalog, can be tracked back to the situation, which gives a powerful method on the label side and on the training side. Now, what are the physical aspects actually? Physical aspects, as I mentioned in the beginning, is in our case the electromagnetic simulation of wave. So wave is a complex thing. Even here we have light. But what is light? Light is electromagnetic energy. So we have electromagnetic component and we have electro and a magnetic component. So we have a complex, it's a complex nature of the wave. And of course, its propagation depends on many factors in the room. And to make this processing real, we have thought about where should this data be generated. And the only solution to do that in our eyes is at the sensor level, which means, for example, at radar on the antenna level, as we can see here in the flow diagram. So doing this on antenna level means you deal about generating an electrical signal, put it through all the process steps to at the end get different things like range gates, velocity gates, and so on to finally receive the point cloud you see here. And again, the A9 scenario with the bluish and reddish colored points on cars, guardrails on the objects, which are actually for radar typically very sparse. And here we have the partners on board with whom together we develop those sensor models which are plugged into this pipeline with an open interface. The interface is already publicly available, and in the discussion in the project is going to be extended with more and more features. So this physical-based sensor processing allows us now in the different work packages, especially in TP1 and TP3, to make here, based on the scenario descriptions, really the comparisons against the recorded real data and data tooling, to make another level of judgment on how can we make synthetic data better compared to the real data. Last step is, of course, physically based rendering has also a downside, unfortunately. It's at the moment very compute intense. Yeah. We use large clusters to render that, and even with the latest technologies, it takes its time. Of course, there's a lot of benefits. However, there might be use cases where we might want to come quicker to more variation, quicker to a result which satisfies the needs. And here, neural rendering techniques are an approach to do that. So what is behind such approach? Well, you render the data once, or you even render it in lower quality, but you use AI-specific methods, again, like GANs, to implement either an impression of the sensor or even exchange the rendering technique itself. For example, in this case, we're taking GANs to prepare the facade textures of the scene to make them look like in reality, to even capture better the light situation, the contrast ranges, the color values, so that this comes closer to what you expect, what you see maybe in real data sets, and make it fast and scalable. And that's also basically my summary here. With this approach of the tool chain we have implemented here, in which we're going to extend in data tooling, gives you a powerful, flexible approach, a toolkit basically, with different modules, which will be later on available as a cloud service to transform and process data for simulation, data for, I would even call it more than SIL testing, more than software in the loop testing, because here we have the AI in the loop. Thanks, and we're looking forward to the next talks.
Yeah, hello. I am André from dSpace, and I fear a little bit that I'm the guy running a little bit out of time now, but I try to keep in time. And what we will have a look at now is what you have seen before, with what we have seen presented by Tom Stone. Already, it's about the evaluation of the synthetic data, especially of the synthetic images. And I want to drive you now through these three first results and these three first findings we had, and we start with the distance metrics. And what is the most important thing, the most important question we want to answer at this step in the whole process? It's the question: what is actually the difference between the synthetic images and the real ones? Because if you know what the gap is, and if you maybe are able to quantify that, then you might be able to know how to change your synthetic images in a way that they become more realistic. And so a first step into the direction to answer this question is to calculate standard distance metrics. And we did that for the sample data of a kitty and V kitty. We applied here as a first step, and as you can see, the behavior of the metrics is quite different. And why is that the case? And I can show you one example. We are looking now at one of the metrics, and as you can see here, we have I have selected three regions here in the plot. There are two which are indicating that in the sequence of the scene here, the frames are quite similar, and here we have a point where the matrix says it's quite unfamiliar, and this is in this case due to the large parts of dark colors here caused by the shadows. And this pair here, although we would say, or it's not too bad, this chosen metric here says it's very different. So what we can learn from that is that each of the applied metrics has its own a focus in the images, and we still do not know how this is related to the outcomes of the neural nets, and whether the object detection takes care about this. And so, as a next step, we compared the distance metrics to the performance of the object detection. And as you can see here, you can have both cases. You can have image pairs which are regarding to this a distance metric quite similar. But if you compare I said it wrong. This is quite similar and close regarding the distance metric, and if you use the IOU to compare the predictions on the images, they are quite distant. And here you have an image pair where this is a vice versa. And a second thing you can observe here is that the data seems to be clustered. So we have the effect that inside a scene, the results of the metrics and the prediction comparison is quite close, but not between the scenes. And the third thing we had a look at is we compared the ground truth of this synthetic VKT data and to the ground truth of the Kitty data. And what you can see here is that and Tom already mentioned it, that you have, of course, in the synthetic data a huge a number of ground truth bounding boxes compared to the real data, and how to deal with that. You should have in mind that here is on the images you can only see the ground truth data, and what we did here is we cleared the ground truth data by calculating the IOU of both ground truth data, and we kept only those ground truth bounding boxes which were close to each other. And the final result from that is the straight lines you can see here are the MIP values per scene in VKT and Kitty. The green line is are the VKT MIPs, and before cleaning the ground truth data, we had much in some of the scenes we had a much a better performance of the object detection in the synthetic data than in the real one. But of course, this is not what we want to. We want to have a performance in the synthetic data which is as good and as bad as in the real one, and you can see it in the dotted lines. Where's this? Don't know. That after cleaning and pruning the ground truth data, in the way I described, we got for most of the scenes nearly the same performance measures than in the real data. And with this, I want to come to an end and just mention again that I wouldn't call this a research, but more first indications, first findings, and first experiences we made with example data. And as soon as we can get our hands on the data coming out of the project, this will guide us through our evaluation studies. Thanks.
So I think the others are already waiting to come for the next. So let me just please only make 2 sentence last comments. First of all, thanks to all the presenters. Was, I think, a really good show, really interesting, very technically very interesting. That was the one point I'm proud of. And the other thing is that I think was also clear, and we could see how good the collaboration actually works here with 4 different partners who presented their results. There are even more who had not the time today to present it, so it's really nice to see this cooperation, how this works. And the other thing is, yeah, actually we have planned to put questions to the people, so now that we cannot do any more, but I hope you entered your question into the app, and we will now have anyway the podium discussion, and I hope that all the presenters from right now, they still keep here, have time to take part in the presentation, and if then specific questions to that deep dive will come, then I think we are very flexible here. Then we could also ask you, hopefully, to come to stage and answer with something special about this data production or analysis. Then we just ask you. Thanks, and then I think we end. And big applause to the presenters, please, again. So.
Gut, sehr gut.
Ich geselle mich noch dazu dann, glaube ich, oder?
Sie haben die Fragen, oder muss ich sie von hier scheren? Okay, alles klar. Good. Then I think it's a Friday afternoon, and the only thing standing between you and a good weekend is us up here. I already took a sneak peek into the tweetback tool. Thanks for the great questions that came in. And I think we have also good voting activity on the questions, so we didn't even have to come up with some trick questions that we have prepared for show reasons, of course. No, we're actually going to now answer your real questions, and we'll put them onto the screen. I think we'll go through them one by one. And there's the first question that was up there is, how does the context data in KIDT relate to the ODD from KIA? And I think, Thomas, context, that goes right to you.
Yeah, thank you for the question. Well, in general, I think the context concept I have presented previously is more a conceptual thing. It's a kind of conceptual framework.
and it's not fixed to any concepts. When I think about the ontology stuff with T boxes and A boxes, the T boxes are not fixed. So I would say they are strongly related, and we are already in the alignment between KIA and KIDT. So I don't know who. Does it already answer the question, or?
Sorry. Yeah, that partly answered the question, so thanks for that already. I'd be interested to hear whether you are already also planning to integrate the Kia ontology or the metadata they read from that into the Kai data tooling project.
Yeah, as I said, there are already have been some alignments with for example, Thomas Stauner. From my point of view, so I'm not responsible for the context stuff. I think we should have a better alignment. So yeah, I hope that we can build up on your already on the work you already did. So that would be in KIA.
It's a great question, and thanks for pointing it out, Martin. That definitely is one of the follow-up and handshake activities that I think need to be brought together. Obviously, from function definition down to selection and searching for data, there is a gap, and that needs to be solved systematically. And the ontologies are a great way of putting in the right semantic layer and the right abstraction. And then I guess it's a follow-up discussion that we're going to have now in KIDT. Right? Second question was looking into auto-labeling. What is preventing auto-labeling? What are the main challenges with the methods of today? And which specific points can be addressed in the near future? I think, Jan, that hopefully was already answered partly in your deep dive. Maybe you had a similar question already that was raised there. But what did you discuss? Okay. Caught entering.
Yeah, thanks. So I wouldn't say there's a lot there are definitely challenges for auto-labeling. And those are, for example, that there are many different sensors. So a sensor can have an influence on your automation capability. There are a lot of different domains. So for example, if you have a highway use case, this is a quite clear one. But then if you want to go to a city, a dense city, or just a completely different geography, this will definitely have an impact on your automation. And also just as simple as day and night. We had this use case that I described in the other deep dive, where we only trained for a POC on day scenes and had a 70% automation rate for this POC. And in the end, we got 2 night scenes, and it dropped by 30% or so our automation rate because we never trained on night data. So domains is definitely the biggest challenge, and a domain gap in that sense. And what was the rest of the question with the current methods?
Well, it's asking for points to be addressed in the future.
Yeah.
And how to improve. Then I guess closing the domain gaps will be.
Exactly, yeah. So once you have enough training data and you trained on enough domains, then you would have a holistic auto-labeling, but then you still have to make sure that you would also train on all of the sensors or get an alignment what kind of sensors should be used. But I guess this is more difficult since every OEM will decide on their own what kind of cameras or LiDARs they want to put in their car.
I mean, obviously, the OEMs in the room were hoping for the answer of getting rid of labeling altogether, right?
I mean, at some point, of course, it's possible, and we are also making quite good progress there. But it's at the moment, so far, it's always use case specific, so you always can fine-tune the automation for a specific use case to a very high level, even 100% automated. But then if you have a completely different domain or another use case, then you would have to start over again. Unless you have done hundreds of use cases, and then maybe at some point.
Oh, great. Thanks a lot for the extensive answer.
Yeah, sure.
Next question is an interesting one as well, because it's looking into autonomous development strategy, but with a very specific focus on collaboration and how to actually share the load. Will there be monoliths such as Tesla or multiple partner collaboration for data collection, model training, validation and testing by different companies? And I think that's an interesting part. Jan, do you want to take that question? Frank, sorry.
No, I can do it. Yep.
Sorry.
No problem, I can do it. So I think it is really easy to answer. I think we will have multiple partner cooperation and collaboration, because I think to follow a monolithic approach is you have a quick start. So this is something what you can reach by using this approach. But I think the needed level of quality which we have to get to involves more specialists you cannot integrate into one company. I do not believe that. And I'm still believing more in cooperation, collaboration as a good ground for and foundation for innovation, I think. In particular because we are still learning how to deal with different technologies and how to integrate them. There's not just one strategy. We have to further discuss this in the next years. And what is also positive is currently that in particular in the automotive industry, by the topics like Gaia X and Catena X, many colleagues are currently working on a foundation for these new types of cooperation and collaboration based on data and models. And I think this will also be an important foundation for further activities in the area of development of automotive driving and that stuff.
Yeah. No, thanks a lot. Obviously, that also touches the question of responsibility and sharing the load, and ultimately then it goes also into the direction of product liability and product safety.
Yeah.
So do you see a future where we'll actually share product liability over the different parts of an AI development cycle? Liability for the data, liability for the tested product, a liability for the trained model?
Yeah, I think we have to. So I think currently, or what we have to do is really to cooperate and collaborate. And if we want to do this, it is obvious that we have also to go into that direction, that we talk more about liability and we have to share things among the value chain in the automotive industry.
I mean, that would be definitely a leap forward from what we're currently doing. Yeah. That will be a fundamental change. Okay. Next question is looking into the synthetic data and how KI upcycling is profiting from it with rich metadata from the very fine-grained semantic dimensions in the ODD. And so there's the examples on the appearance of pedestrians. And the question is, do you plan to generate such fine-grained metadata for real data or real data as well? And will this be automated or manual? And I think, Armin, that question partially goes into your direction, right? Or you actually would be very well suited to answer it.
Yes, yeah. Yeah, definitely. We will, since I think for those who participate in the synthetic data presentations, you saw that we proceed with using and even optimizing the tool chain for the synthetic data, so that will continue. So we will still have the same partners on the boat with bit technology, with Macrovision, with Intel. We currently speaking how we could collaborate in future, even if there are no partners. So that will definitely all the stuff we want to, of course, use and even optimize and push further. And in addition to that, yeah, we got new partners like we've seen today, dSpace, but ANSYS, and also to mention FKFS.
less important role, so they were not participating in the presentation, but the poster was there. They keep all together with the architecture, bring the traffic simulation there. So we will build out that tool chain, of course, and all what is already there will be used, of course. And we've also seen, I think, if I remember right, in KI-Absicherung, there were some ground truth and metadata, what the one producer was able to support and the other ones not. And that's really what we think about, that we make this more to a standard that everybody and that who participates in the tool chain can produce the same things. So therefore, what we had a discussion, there were regular meeting, called it Synthetic Data and Tool Strategy meeting, where also Thomas Stauner joined. And now to the end, we set up a kind of backlog. Actually, we collected all open tool optimization topics, put it in a backlog, and got some recommendations from KI-Absicherung what we should do, and then we will rate that and we'll do this on the outcome, on the priority that comes out. We will implement that.
Thanks, Armin, for the answer to that question. And yes, I was just about to hand over to the real data part, right? Because Marcel, from the real data that you saw so far, do you think with what the plans in synthetic data are, will we be able to generate the digital twins that we need at large there?
About the digital twins, I think Armin is the expert, but what I can say is we have a specification for the metadata, which is built up on the specification of KI data tooling, and we apply this specification as most as possible automatically. Yeah. Okay. We have a tool chain already, and we can generate a lot of metadata.
Yeah, and so I think the limitation will be to generate the fine-grained metadata also for all the real data that we collected so far. I think that so far has not been the plan, but we definitely need to look into it with the limitations on the digital twins. Yeah.
Okay.
Okay. Next one is obviously also dealing with data, but from a different angle. It's asking about test data and in continuous delivery and testing, raising the issue of slow overfitting of data by the constant reuse of test data. So Tom, how often do you plan to reuse test data in training your models?
Of course, as much as possible, but also I think it's something, our data sets will never be kind of finished in one way or another, and they will be very large. So to answer it, probably too simple, but I guess we won't have a problem there. I think the ODD is very complex there to span it up even to some amount that is useful for us. We're going to have, I don't think we're going to ever, we're not going to run into that problem, I guess, if I understood the question right.
So is the variability of synthetic data going to help?
Yes. Yeah, I think so. So in the end, I don't. I mean, our strategy is to use synthetic and real data, and also never, like I said, we're never going to have something like a finished data set. I guess it's always going to be something growing to some degree, at least, or at least spanning the ODD better and more suitable for our the downstream tasks that we have at hand to train. So. I think the mixture strategy we're working on is going to solve that problem if we would ever run into that.
Okay, thank you very much.
The question was from me, and I think he didn't understand it correctly.
That could be.
Oh, of course, yes.
Thank you. Hi, Alexander Hirsch from Bosch. So the question actually goes into the direction, if you're reusing the test data in your continuous delivery or continuous testing cycle, you will slowly overfit to the test data because you're reusing it all the time, and you're making small decisions when reusing the data because probably you have multiple models and the model's changing over time, and you will keep the best model which fits best to this test set, right? And even if you only have a pass-fail feedback, it's some kind of cycle, or you have a feedback loop in there, right? And you're slowly overfitting to this data. And the question arises, how often can you reuse the data? I mean, it's a trade-off between unseen data and the credibility of this data, and then cost, right? And that's the point of the question.
Well, let me ask the question the other way around. If the test data accurately sample the ODD, wouldn't the creep that we see actually be desirable?
That's correct as well. So there's a temporal component to this question as well, because at some point in time the reality changes, right? We have these e-scooters, for example. We didn't have them 5 years ago or something like that. And this is also a limitation where you have to make a decision when to throw away your test data.
And like I said, I think in that case, our data set will never be finished. Like you said with the e-scooters, I think our data set is something that is never going to be stable in one way or another. I hope I don't break any safety assurance things there, but I guess we will never stop to refine it. We have to actually, we need something to be constantly refining it because of the e-scooters, and not only that, lately we saw things like more bikes with something in the front or in the back where there are kids or dogs in there. So there's constantly something new coming up where we probably will never stop even changing the test data. Actually, that's my wish. We shouldn't stop because there's always something coming up. And if you stop for a minute to see what is changing in the world, you will probably have problems like this, where you just miss new things happening. So it's probably going to be a new refinement step, like in a constant cycle.
But if you think about Tesla that is pushing updates on a weekly or monthly basis, and you want to validate your function before you put it to the customer, you're probably not getting that much data in that short amount of time to revalidate your model all over again, right?
Either future work, or we have to think about how to solve this in the current project.
Okay, thank you.
If you have a good tip, hint.
But it's a great question. Thanks a lot for it. And it just brought a picture up in my head where I see all of us annually watching the Paris fashion shows for the latest clothing styles that we need to introduce into our training and test data. Okay, Andreas, you already came up to the panel because I think the next question really perfectly goes into your direction on how data-driven development compares to the dSpace ML model extension. It's about process quality, and I think you're perfectly positioned to answer it, hopefully.
I hope so. Sorry, I forgot to stand up, and the day was long. Well, next week I'm going to present a similar thing on the VDA Automotive Sys, and this is the place where we'll also discuss this in detail. We have tried to push this already towards the dSpace gremium. As far as I know, this new standard is driven by a consultant agency, Kugler-Mark, and maybe they've collected from all their consultancies with different companies what should be maybe the right standard. But we don't think that this comes really from the practice. So our approach is really meant for a serious process from someone who will do this in large scale. And we have tested this with our Athena framework those days and automated this in several stages to see if this is doable. And we believe that our process is much closer, process approach is much closer at that what we really need. And we will try to defend this and push it. And I'm sure that there will be some overlap where we could align and find some commonalities where we, let's say, have a standard in the end, hopefully, which considers both aspects if possible. But I also try to prevent that, I would like to try to prevent that someone from outside forces us to do something which is not helpful in practice. I try to emphasize that this was really developed by developers, so it would help us, not hinder us in some ways. And we will analyze this in detail and discuss it and see where we could maybe change some things. But it will be a fight, I guess, and because there's other interests behind, and we will see next week what comes out.
Good luck with the discussions, and obviously with many practitioners and researchers in the room, we hopefully see the support for the practitioners growing, right?
But I personally very much believe that our approach works.
Yeah.
But if something doesn't work, we are the last ones who wouldn't change it. We will make it fit to our needs, and this is the most important thing. It must work in practice, and I guess we will do this.
Yeah. And in the end, there needs to be convergence. It doesn't help anybody with two conflicting standards. Yeah, I think we have addressed the questions with most of the likes so far. Maybe just for the final round, did we, or did anybody in the room now develop another question that you would like to ask now? We can hand out the microphone, of course, for the final round before we close today. Any questions left in the room today? Except, when do we close? Right now. So thank you very much for everybody. Thanks for the presenters, for the panel. Thanks for staying late on a Friday afternoon. I think that's also not something quite in the ordinary. I very much enjoyed the discussions and the lively debates today. And I'm looking forward to picking up on the challenge questions now. There's already some forward debate that we can sense here. And we hope to stay in touch with each and everyone, and don't see you back in 1.5 years for the final event, but hopefully for some workshops in between. And we'll hopefully receive good feedback also from the discussions also in the standardization committees with all the good work that has been started now, and that's also something that we will try to contribute a lot from the KIDT project. We'll keep you posted. Thank you very much. Have a safe trip home. Bye-bye.